One day, the very reason behind our existence will betray us. That golden disk hanging in the morning sky, the same celestial body that coaxed the first single-celled organisms out of the primordial soup, that guided ancient navigators across endless oceans, that warmed your face on that perfect summer afternoon you still remember. One day, it will swell into something monstrous. It will grow so enormous, so hungry, that it will reach across millions of kilometers of space and devour the inner planets of our solar system. Mercury will vanish first, vaporized in an instant. Venus, that scorching hell world shrouded in sulfuric clouds, will follow shortly after. And then perhaps our home, this pale blue dot we call Earth, will meet the same incandescent fate. Sounds terrifying, doesn't it? Like something out of a fever dream or a doomsday prophecy. But this isn't science fiction. This isn't speculation. This is the inevitable future written into the very physics that govern our universe. The sun, that eternal fixture we have taken for granted since the dawn of human consciousness, is going to die. But here's the thing about cosmic endings. They're rarely simple. The death of our star isn't a single event, but rather a drawn-out transformation spanning billions of years, a metamorphosis so dramatic and so violent that it will reshape everything we have ever known about our corner of the cosmos. And yet, paradoxically, within this destruction lies a strange kind of beauty, a cosmic recycling program that has been creating and destroying worlds since the universe was young. Before we embark on this journey through time and space, through the fiery heart of our star, and out into the cold darkness that awaits beyond, let us pause to consider what we're really talking about. We're not simply discussing an astronomical event that will occur in some impossibly distant future. We're contemplating the end of everything that has ever mattered to our species. Every sunrise and sunset, every photosynthesizing plant, every warm day and starlit night. We're contemplating what happens when the cosmic engine that powers all life on Earth finally runs out of fuel. The sun, you see, is far more than just a bright object in the sky. It is a thermonuclear furnace of almost incomprehensible scale, a roiling sphere of plasma so massive that it contains 99.86% of all the matter in our entire solar system. If you could hollow it out, you could fit 1.3 million Earths inside it and still have room to spare. Every single second, this magnificent stellar engine converts roughly 600 million metric tons of hydrogen into approximately 596 million metric tons of helium. The remaining 4 million metric tons, they don't simply disappear. They are transformed into pure energy according to Einstein's famous equation, E equals mc squared, released as light and heat that streams outward in all directions at nearly 300,000 kilometers per second. This energy is what makes life possible. It drives the water cycle that brings rain to our crops. It powers the photosynthesis that fills our atmosphere with breathable oxygen. It maintains the delicate temperature balance that keeps our oceans liquid and our planet habitable. Without it, Earth would be nothing more than a frozen rock hurtling through the void, as lifeless and barren as any asteroid. And yet, as permanent as the sun may seem from our brief human perspective, it is anything but eternal. Our star was born approximately 4.6 billion years ago from a collapsing cloud of gas and dust, and it has been steadily burning through its hydrogen fuel ever since. Right now, at this very moment, the sun sits comfortably in what astronomers call its main sequence phase, a period of relative stability during which it fuses hydrogen into helium in its core, generating the outward pressure needed to counterbalance the inward crush of its own gravity. But nothing lasts forever. Not empires, not mountains, not even stars. The sun has already consumed about half of its usable hydrogen fuel. In another 5 billion years or so, a span of time so vast it makes the entire history of human civilization look like the blink of an eye, the hydrogen in the core will finally be exhausted. And when that happens, everything changes. The delicate equilibrium that has kept our star stable for billions of years will be disrupted. Forces that have been held in check will be unleashed, and our sun will begin its long, spectacular descent into death. This script is an exploration of that death and of the many other ways our solar system could meet its end. Because while the sun's natural demise billions of years from now represents the most likely scenario, it is not the only possibility. The universe is a violent and unpredictable place, filled with wandering stars and gravitational chaos that could disrupt our comfortable existence far sooner than we might expect. Over the course of this journey, we will examine 3 distinct scenarios for the end of our solar system as we know it. First, we will explore the sun's natural death, the slow, majestic transformation from a middle-aged yellow star into a bloated red giant, and eventually into a tiny, dense, white dwarf. This is the fate that awaits our star, according to the well-established physics of stellar evolution, a process that plays out over billions of years and will fundamentally transform the inner solar system. Second, we will conduct a thought experiment, a purely hypothetical scenario that asks what would happen if the sun simply vanished. Not in a supernova explosion, not in a slow fade, but an instantaneous disappearance that defies the laws of physics as we understand them. This impossible scenario, while never going to actually occur, allows us to examine just how dependent Earth and all its inhabitants truly are on our parent star. It reveals the fragile thread by which all life hangs. Third, we will examine the very real threat posed by stellar encounters. The possibility that another star could wander too close to our solar system and disrupt the delicate gravitational balance that keeps our planets in their orbits. This is not science fiction. Stars are not stationary fixtures in the sky, but rather objects in constant motion, careening through the galaxy at hundreds of thousands of kilometers per hour. Some of them are already heading in our direction. Each of these scenarios offers its own revelations about the nature of stars, the mechanics of planetary systems, and the ultimate fate of life on Earth. Each forces us to confront uncomfortable truths about our place in the cosmos and the temporary nature of everything we hold dear. But this exploration is not meant to inspire despair. Quite the opposite. By understanding how our solar system might end, we gain a deeper appreciation for the remarkable circumstances that allow it to exist at all. We come to see our sun not as an unchanging constant, but as a dynamic, evolving object with its own life cycle, a life cycle that happens to have produced the conditions necessary for us to be here, asking these very questions. The story of our sun's death is, in a very real sense, the story of cosmic recycling. The elements forged in its core and expelled into space during its final throes will one day become the raw materials for new stars, new planets, and perhaps new life. The carbon in your body, the oxygen you breathe, the iron in your blood, all of these were created inside ancient stars that died billions of years before our sun was born. We are quite literally made of stellar ash, and one day our sun will contribute its own material to this great cosmic cycle. So let us begin this journey with open eyes and curious minds. Let us travel to the heart of our star and witness the nuclear fires that have burned for billions of years. Let us watch as those fires slowly fade and the sun begins its transformation into something vast and terrifying. Let us stand on the frozen surface of an Earth abandoned by its star, and let us contemplate what strange forms of life might persist even in that endless darkness. The sun is going to die. But in that death, as in all deaths, there is the seed of something new. The end of our solar system is not truly an ending at all. It is a transformation, a transition, a passage from one state of being to another. And that, perhaps, is the most remarkable thing of all. The night sky seems peaceful and orderly from where we stand. Those pinpricks of light appear fixed and eternal, unchanging constellations that have guided human beings for thousands of years. But that appearance of stillness is an illusion born of our limited perspective. In reality, every single one of those stars is moving. They are careening through the galaxy at speeds that would make our fastest spacecraft look like they were standing still. The stars of the Milky Way are not bound by static formations but are constantly changing cosmic neighborhoods. Fortunately, space is incomprehensibly vast. The distances between stars are so enormous that collisions are almost impossibly rare. Our nearest stellar neighbor, Proxima Centauri, sits more than 4 light-years away, roughly 40 trillion kilometers of empty space separating us from the next closest sun. At such distances, direct impacts between stars are about as likely as 2 gnats colliding in the Grand Canyon. But here's the troubling reality. Stars don't have to actually hit anything to cause catastrophic problems for our solar system. They don't have to touch us to ruin everything we know. Gravity, that invisible force that holds planets in their orbits and keeps your feet planted on the ground, extends across the cosmos in all directions. Every piece of matter in the universe attracts every other piece of matter. You are, right now, being gravitationally attracted to a distant star 1,000,000 light-years away. And that star is being attracted to you in return. Luckily, gravitational force weakens dramatically with distance, and it depends heavily on mass. The more massive an object, the stronger its gravitational pull. This means that close, massive objects exert far more influence than distant, lighter ones. It's why you feel the Earth's gravity so strongly, and the Sun's gravity hardly at all, even though the Sun is vastly more massive. It's simply too far away for its pull to dominate your daily experience. This relationship between mass, distance, and gravitational influence is what keeps our solar system stable. The Sun, containing 99.86% of all the mass in our celestial neighborhood, dominates everything. Its gravity shapes the behavior and orbits of all 8 planets, the dwarf planets, the asteroids, the comets, and every tiny speck of dust that circles within its domain. Everything else in the solar system is, gravitationally speaking, just along for the ride. But what happens when another massive object intrudes into this carefully balanced system? What happens when a wandering star comes close enough for its gravity to challenge the Sun's dominion? That is a question we will explore in detail later in this script. For now, let us turn our attention to the Sun itself, to understanding what it is, how it works, and why its eventual demise is not just possible, but absolutely certain. Because to truly comprehend the death of our star, we must first understand its life. From our vantage point here on Earth, the Sun appears almost placid. We see it rise each morning as a glowing orange disk, climb to its zenith as a brilliant white sphere too bright to look upon directly, and sink each evening in spectacular displays of red and gold. It seems constant, reliable, unchanging. a fixed point around which our lives revolve with the same predictable regularity as the Earth's orbit. But appearances, as they so often are in astronomy, are deceiving. Up close, the sun is anything but calm. It is, in fact, the most turbulent and violent place in our entire solar system, a churning inferno of superheated plasma, raging magnetic storms, and nuclear explosions that dwarf anything humanity has ever conceived. Viewed through specialized telescopes that filter out the blinding glare, the sun reveals itself as a dynamic, constantly evolving sphere of controlled chaos. Sunspots larger than Earth drift across its surface. Massive loops of plasma, called prominences, arc hundreds of thousands of kilometers into space. Coronal mass ejections blast billions of tons of charged particles outward at millions of kilometers per hour. And deep in its core, where temperatures exceed 15 million degrees Celsius and pressures reach 265 billion times the atmospheric pressure at Earth's surface, the most powerful energy-generating process in the known universe is taking place: nuclear fusion. Let us begin with the raw numbers, because the sun's statistics are almost impossible to comprehend without them. Our star has a mass of approximately 1.989 times 10 to the 30th power kilograms. Written out in full, that's about 1,189,000 kilograms, nearly 2 nonillion kilograms of mostly hydrogen and helium plasma. This represents roughly 333,000 times the mass of Earth. If you placed our planet on one side of an impossibly large cosmic scale, you would need to stack more than 1/3 Earths on the other side just to achieve balance. The sun's diameter stretches approximately 1,391,400 kilometers from one edge to the other, about 109 times the diameter of Earth. This means that if you could somehow hollow out the sun and keep its spherical shape, you could fit roughly 1.3 million Earth-sized planets inside it. Picture that for a moment, over 1 million worlds like ours, packed together inside a single star. The surface temperature of the sun, what astronomers call the photosphere, hovers around 5,500 degrees Celsius, or roughly 5,800 Kelvin. That's hot enough to vaporize any known material, to reduce steel and stone and diamond to their constituent atoms. But the surface is actually the coolest part of the sun that we can observe. Move inward, and temperatures climb dramatically. The chromosphere, a thin layer just above the photosphere, reaches temperatures of about 20,000 Kelvin. The corona, that ghostly halo visible during total solar eclipses, paradoxically soars to temperatures exceeding 1 million Kelvin, a mystery that scientists are still working to fully explain. And then there is the core, at the very center of the sun, where the full weight of that 2 nonillion kilograms of plasma presses inward from all directions. Conditions are almost beyond imagination. The temperature reaches approximately 15 million Kelvin, about 27 million degrees Fahrenheit. The density climbs to about 150 grams per cubic centimeter, roughly 8 times denser than gold and 13 times denser than lead. The pressure exceeds 26.5 billion gigapascals. These are conditions that exist nowhere else in our solar system, conditions so extreme that they make the hottest places on Earth seem like frozen wastelands by comparison. It is in this hellish environment that the sun generates its power. The process is called nuclear fusion, and it is fundamentally different from the chemical combustion that powers everything from campfires to rocket engines. When you burn wood or gasoline, you are breaking and reforming chemical bonds between atoms, releasing energy stored in the molecular structures. The atoms themselves remain unchanged. Carbon is still carbon, hydrogen is still hydrogen, oxygen is still oxygen. Nuclear fusion is something far more profound. It involves forcing atomic nuclei, the dense, positively charged cores of atoms, to merge together, creating entirely new elements in the process. This is not chemistry. It is alchemy made real. The sun is literally transmuting hydrogen into helium, transforming one element into another through sheer force of temperature and pressure. Here is how it works. The sun's core is composed primarily of hydrogen in its plasma state, meaning the atoms have been stripped of their electrons by the extreme heat, leaving behind bare nuclei called protons. These protons are all positively charged, which means they naturally repel one another through the electromagnetic force. Under normal circumstances, this mutual repulsion would keep them forever apart, like magnets pushing against each other with their similar poles facing. But the conditions in the sun's core are anything but normal. The temperature is so high that the protons are moving at tremendous velocities, hundreds of kilometers per second. The density is so extreme that collisions between protons occur with staggering frequency. And the pressure is so intense that the protons are forced into incredibly close proximity despite their electromagnetic repulsion. When two protons approach each other closely enough, within about 1/quadrillionth of a meter, something remarkable happens. A force called the strong nuclear force takes over. This force, which operates only at extremely short ranges, is far more powerful than the electromagnetic repulsion that was keeping the protons apart. It grabs onto the protons and fuses them together, binding them into a new nucleus. This fusion process doesn't happen in a single step. The sun uses a series of reactions called the proton-proton chain, a cascade of nuclear transformations that ultimately converts 4 hydrogen nuclei into 1 helium nucleus. Let me walk you through this cosmic assembly line. In the first step, 2 protons collide and fuse together. One of the protons immediately transforms into a neutron through a process called beta plus decay, releasing a positron, an antimatter electron, and a neutrino. The result is a nucleus containing 1 proton and 1 neutron. This is deuterium, also known as heavy hydrogen. In the second step, the deuterium nucleus collides with another proton, fusing to create a nucleus with 2 protons and 1 neutron. This is helium-3, a lighter isotope of helium. In the third step, 2 helium-3 nuclei collide and fuse, producing a nucleus with 2 protons and 2 neutrons, regular helium-4, while ejecting 2 excess protons back into the plasma to participate in future reactions. The net result of this entire chain, 4 hydrogen nuclei have been converted into 1 helium nucleus, plus various byproducts including energy. But where does the energy come from? Here's the key. A helium-4 nucleus is slightly less massive than the 4 hydrogen nuclei that created it. Specifically, about 0.7% of the original mass has gone missing. This mass hasn't simply vanished. It has been converted into energy according to Einstein's famous equation, E equals mc squared. The c in that equation represents the speed of light, about 300,000 kilometers per second. When you square that number, you get an enormous figure. This means that even a tiny amount of mass converts into a tremendous amount of energy. That missing 0.7% of mass from each fusion reaction is what powers the sun, and the sun is fusing a lot of hydrogen. Every single second, approximately 600 million metric tons of hydrogen are converted into roughly 596 million metric tons of helium in the sun's core. The difference, about 4 million metric tons of matter, is transformed into energy. That's 4 million metric tons of mass converted into pure energy every second of every day, year after year. for billions of years. To put this in perspective, the largest nuclear bomb ever detonated by humanity, the Soviet Tsar Bomba, released about 210 petajoules of energy. The sun releases approximately 384 yotajoules per second. That's equivalent to exploding about 1.8 billion Tsar bombas every single second. And the sun has been doing this continuously for 4.6 billion years. This energy radiates outward from the core in all directions. But its journey to the surface is neither quick nor direct. The core is surrounded by a region called the radiative zone, where energy travels outward as electromagnetic radiation, primarily X-rays and gamma rays. However, the plasma in this region is so dense that photons can travel only a short distance before being absorbed and re-emitted by an atom. Each photon bounces from atom to atom in a random walk that gradually carries it outward. How long does this journey take? Estimates vary, but most calculations suggest that a photon produced in the sun's core takes somewhere between 100,000 and 170,000 years to reach the surface. Let that sink in. The sunlight warming your face today was generated in the sun's core around the time that anatomically modern humans were first emerging in Africa. Beyond the radiative zone lies the convection zone, where the plasma becomes less dense and energy is transported not by radiation, but by the physical movement of hot material. Massive convection cells carry heated plasma upward toward the surface, where it releases its energy, cools, and sinks back down to be reheated. This convective churning is what creates the granulated appearance of the sun's surface, a pattern of roughly 1.5 million convection cells, each about 1,000 kilometers across, constantly rising, cooling, and sinking. All of this, the fusion, the radiation, the convection, the incredible release of energy, exists in a state of delicate equilibrium. The sun is essentially a controlled thermonuclear explosion, one that has been burning steadily for billions of years because two opposing forces are perfectly balanced against each other. On one side is gravity. The sun's enormous mass creates a gravitational field that constantly tries to crush the star inward to compress all that plasma into an ever smaller, ever denser ball. Gravity never stops pulling, never takes a break, never gives up trying to make the sun collapse. On the other side is radiation pressure and thermal pressure generated by the nuclear fusion reactions in the core. The energy produced by fusion heats the plasma to tremendous temperatures, causing it to push outward against gravity's inward pull. As long as fusion continues, this outward pressure exactly counterbalances gravity's inward force, maintaining the sun's size and stability. This equilibrium is self-regulating in a remarkably elegant way. If fusion were to suddenly increase for some reason, the extra energy would heat the core, increasing the outward pressure. This would cause the core to expand slightly, but expansion would lower the density and temperature, which would reduce the fusion rate, which would reduce the pressure, causing the core to contract back to its original size. The same feedback loop works in reverse. If fusion decreased, the core would contract, heat up, and fusion would increase again. This thermostat has kept the sun stable for 4.6 billion years, and it will continue to keep it stable for approximately another 5 billion years. During this time, the sun exists in what astronomers call the main sequence, the long, stable phase of stellar life during which a star fuses hydrogen into helium in its core, but the equilibrium is not eternal. It cannot be, because the sun is slowly, inexorably running out of hydrogen fuel. Every second, 600 million metric tons of hydrogen become 596 million metric tons of helium. That helium accumulates in the core like ash in a furnace. It doesn't participate in the proton-proton chain because helium fusion requires far higher temperatures than hydrogen fusion, temperatures the sun's current core cannot achieve. So the helium just sits there, building up, gradually increasing the core's mass and density while decreasing its hydrogen content. Right now, after 4.6 billion years of fusion, the core has converted roughly half of its original hydrogen into helium. The sun is, in stellar terms, middle-aged. It has passed the halfway point of its main sequence lifetime, but still has billions of years of stable hydrogen burning ahead. During this main sequence phase, the sun is slowly getting brighter. The accumulating helium makes the core slightly denser, which causes it to contract slightly under gravity's pull. This contraction heats the core, which increases the fusion rate, which increases the sun's energy output. Over the past 4.6 billion years, the sun's luminosity has increased by about 30%. It will continue to increase by about 1% every 100 million years. This gradual brightening has consequences for Earth. In about 1 billion years, long before the sun reaches the end of its main sequence phase, it will have become bright enough to trigger a runaway greenhouse effect on our planet. The oceans will begin to evaporate. The water cycle will break down. Complex life will become impossible. In about 3 to 4 billion years, the oceans will have evaporated entirely, and Earth will become a Venus-like hellscape of searing temperatures and crushing atmospheric pressure. But even this is just the beginning of the end. The real transformation, the spectacular death throes of our star, won't begin until the hydrogen in the core is finally exhausted, approximately 5 billion years from now. When that happens, the equilibrium that has sustained the sun for so long will be broken. The fusion reactions will cease. The outward pressure that held gravity at bay will disappear, and forces that have been held in check for billions of years will finally be unleashed, setting in motion a series of events that will transform our solar system beyond recognition. The sun's happy days, as stable as they seem from our brief human perspective, are numbered, and when they end, nothing in our cosmic neighborhood will ever be the same. In the grand cosmic scheme, our sun is remarkably ordinary. It is a G-type main sequence star, also known as a G2V in stellar classification, a yellow dwarf that sits comfortably in the middle of the size and temperature ranges for stars in our galaxy. It is not among the massive blue giants that burn through their fuel in mere millions of years, nor is it one of the tiny red dwarfs that can smolder for trillions of years. It is, by most measures, an average star in an average location in an average spiral galaxy, and like all average stars of its type, it will die in an average way. Stellar evolution, the study of how stars change over their lifetimes, is one of the most well-established fields in modern astrophysics. Through more than a century of observations, theoretical calculations, and computer modeling, scientists have pieced together a remarkably detailed picture of how stars are born, how they live, and how they die. The physics involved, nuclear fusion, gravitational collapse, radiation transport, quantum mechanics, are complex but well understood, and the predictions these physics make about stellar behavior have been confirmed again and again by observations of stars at every stage of their life cycles. This means we can predict the future of our sun with considerable confidence. Not down to the exact year or century, of course. The timescales involved span billions of years, and our models contain uncertainties. But the broad strokes of the sun's future are well established. We know what phases it will pass through. We know approximately when those transitions will occur. and we know what the solar system will look like at each stage. The story begins, as all stellar death stories do, with the exhaustion of hydrogen fuel in the core. Remember that delicate equilibrium we discussed: gravity pulling inward, fusion pressure pushing outward, the two forces perfectly balanced. That balance depends entirely on the nuclear fusion reactions taking place in the core. Those reactions are what generate the energy that creates the outward pressure. Without them, there is nothing to stop gravity from crushing the star. The sun's core has been fusing hydrogen into helium for 4.6 billion years. During that time, it has converted roughly half of its core hydrogen into helium. The remaining half will be consumed over the next approximately 5 billion years, assuming the fusion rate remains relatively constant. After that, the hydrogen in the core will be effectively depleted, not completely gone, but reduced to the point where fusion can no longer proceed at a rate sufficient to support the star. When that moment arrives, the core faces a crisis. The nuclear fusion reactions that have sustained the sun for billions of years will sputter and fail. The outward pressure that held gravity at bay will begin to diminish, and gravity, patient and relentless, will finally gain the upper hand. But here is where things get interesting. The shutdown of core hydrogen fusion doesn't mean the end of all fusion in the sun. It simply means the end of fusion in the core. Remember, the core is surrounded by vast quantities of hydrogen-rich material in the outer layers of the star. This hydrogen is too cool to fuse under current conditions. It sits far above the hot, dense center where fusion takes place. But as the core contracts under gravity's increasing dominance, the situation changes. When the core contracts, it heats up. This is a basic principle of physics. Compress a gas, and its temperature rises. The gravitational energy released by the collapsing core is converted into thermal energy, raising temperatures throughout the core region. And as the core shrinks and heats, the layer of hydrogen immediately surrounding it, the hydrogen shell, begins to experience conditions hot and dense enough for fusion. This is the birth of shell hydrogen burning, and it marks the beginning of a radical transformation in the sun's structure. Shell burning is a fundamentally different beast than core burning. In a main sequence star like the present-day sun, fusion occurs throughout a relatively large central volume. The reaction rate is self-regulating. If things get too hot, the core expands and cools, slowing the reactions back down. But in shell burning, the fusion takes place in a thin layer wrapped around a non-fusing core. The geometry is different. The feedback mechanisms work differently, and the consequences are dramatic. As the hydrogen shell burns, it dumps helium ash onto the core below, making the core more massive and denser. This causes the core to contract further and heat up more, which accelerates the shell burning, which dumps more helium onto the core, which causes more contraction. It's a self-reinforcing cycle that drives changes in the star at an accelerating rate. Meanwhile, something strange happens to the star's outer layers. As the shell burning intensifies and dumps ever more energy into the star's interior, that energy has to go somewhere. It pushes outward against the layers above, heating them and causing them to expand. And because those outer layers are expanding into empty space with relatively little resistance, the expansion can be enormous. The sun, having spent billions of years as a relatively compact yellow dwarf, will begin to swell. At first, the expansion will be gradual. Over the course of about 1 billion years, the sun will grow larger and cooler, shifting from the main sequence toward a region of the Hertzsprung-Russell diagram called the subgiant branch. During this phase, the sun will approximately double in size, while its surface temperature drops by several hundred degrees. It will appear slightly larger and more orange in color, a subtle change, but one that will alter the conditions on whatever planets remain in orbit. But the subgiant phase is just a prelude to something far more dramatic. As the core continues to contract and the shell burning continues to intensify, the rate of expansion will accelerate. The sun will grow larger and larger, its outer layers puffing outward like a balloon being slowly inflated. Its surface temperature will drop further as the expanding gas cools, shifting the star's color from yellow-white to orange to deep red. This is the red giant phase, and it will transform our sun into something almost unrecognizable. At its maximum extent, the sun will expand to roughly 200 times its current radius, possibly even larger. Right now, the sun's radius is about 695,700 kilometers. As a red giant, it will stretch to approximately 150 million kilometers or more. For reference, Earth currently orbits the sun at a distance of about 150 million kilometers. This means the expanded sun will extend roughly to where Earth's orbit is today, perhaps even beyond. Mercury will be the first casualty. At just 58 million kilometers from the sun, it has no hope of escaping. The expanding solar atmosphere will engulf it completely, and friction with the solar gas will cause Mercury to spiral inward, falling ever deeper into the dying star until it is completely destroyed. Venus will follow. At 108 million kilometers, it too lies well within the reach of the red giant sun. Like Mercury, it will be swallowed by the expanding stellar envelope, spiraling inward to its destruction. Earth's fate is less certain, a matter of ongoing scientific debate. The complicating factor is that the sun will lose a substantial portion of its mass during the red giant phase. Stellar winds, streams of particles flowing outward from the sun's surface, will carry away perhaps 30 to 40% of the sun's total mass over the course of its red giant evolution. As the sun loses mass, its gravitational grip on the planets will weaken, and the planets' orbits will expand outward. This expansion might save Earth. Some models suggest that Earth's orbit will expand fast enough to stay ahead of the swelling sun, keeping our planet just beyond the lethal envelope. But other models suggest it won't matter. Even if Earth avoids being physically engulfed, the proximity to the red giant sun will be catastrophic. Surface temperatures will soar to over 2,000 degrees Celsius. The oceans will have long since evaporated. The atmosphere will be stripped away. The rocks themselves will begin to melt. Earth, even if it survives as a physical body, will be sterilized and scorched beyond any hope of habitability. But let us return to what's happening inside the dying star, because the real drama is taking place in the core. As the outer layers expand into the red giant phase, the core continues its relentless contraction. More and more helium ash accumulates from the shell burning above. The density climbs higher and higher. The temperature rises toward the threshold required for a new fusion reaction, the fusion of helium into carbon. Helium fusion is far more difficult than hydrogen fusion, where hydrogen fusion requires temperatures of about 15 million Kelvin. Helium fusion requires temperatures of approximately 100 million Kelvin, almost 7 times hotter. This is because helium nuclei carry twice the electric charge of hydrogen nuclei, 2 protons instead of 1, so the electromagnetic repulsion between them is much stronger. It takes far more kinetic energy, far higher temperatures, to overcome that repulsion and bring helium nuclei close enough for the strong nuclear force to bind them together. For most of the red giant phase, the contracting core remains below this threshold. The temperature climbs toward 100 million Kelvin, but hasn't quite reached it. Helium fusion hasn't begun. The core continues to contract and heat under gravity's relentless pressure. And then something remarkable happens. As the core contracts beyond a certain point, the electrons in the core plasma begin to behave in strange ways dictated by quantum mechanics. A principle called the Pauli exclusion principle states that no two identical fermions, a category that includes electrons, can occupy the same quantum state. As the core is compressed to higher and higher densities, the electrons are forced into ever smaller volumes, and the number of available quantum states begins to run out. At this point, the electrons begin to exert a new kind of pressure: quantum degeneracy pressure. Unlike thermal pressure, which depends on temperature, degeneracy pressure depends only on density. The electrons resist being squeezed any further, not because they're moving fast and colliding, but simply because the laws of quantum mechanics forbid them from occupying the same quantum state. They're like two colleagues who sincerely hate each other, refusing to share the same office no matter how much management insists. This electron degeneracy pressure halts the contraction of the core, at least temporarily. The core becomes what physicists call a degenerate gas, a bizarre state of matter that behaves very differently from the ordinary plasma in the rest of the star. But here's the crucial point. While degeneracy pressure can halt the contraction, it cannot prevent heating. Energy continues to flow into the core from the shell burning above. The temperature continues to rise. And because the core is degenerate, it cannot expand to relieve this temperature increase the way a normal gas would. Eventually, the core temperature reaches the magic threshold, approximately 100 million Kelvin. At this temperature, helium fusion finally becomes possible. 3 helium nuclei can fuse together to form a single carbon nucleus through a process called the triple alpha reaction, so named because helium nuclei are also known as alpha particles in nuclear physics. But the ignition of helium fusion in a degenerate core is not a gentle process. In a normal gas, the onset of fusion would cause the gas to heat up and expand, which would moderate the fusion rate. But in a degenerate gas, the pressure doesn't depend on temperature, only on density. So when fusion begins, the temperature skyrockets, but the core doesn't expand. The rising temperature accelerates the fusion rate, which produces more heat, which further accelerates the fusion rate. The result is a thermonuclear runaway known as the helium flash. In a matter of minutes, a cosmically insignificant span of time, the core releases an enormous burst of energy. During this brief period, the helium flash generates roughly 100 billion times the sun's current luminosity. More energy is produced in those few minutes than the entire Milky Way galaxy produces under normal circumstances. But remarkably, this cataclysmic event goes almost unnoticed at the stellar surface. The energy of the helium flash is absorbed by the layers above the core, going into lifting the degeneracy of the core electrons rather than radiating outward. The temperature spike finally becomes high enough to transform the degenerate core back into an ordinary gas. The core expands, the runaway fusion halts, and a new equilibrium is established, this time with helium fusion proceeding steadily in the core. The sun has survived its helium flash. A new chapter of its life has begun. With stable helium burning established in the core, the sun's internal structure changes once again. The core is now converting helium into carbon through the triple alpha process, generating energy that supports the star against gravitational collapse. The outer layers, no longer pumped up by the intense shell burning that characterized the red giant phase, contract somewhat. The Sun shrinks and heats up, moving to a region of the Hertzsprung-Russell diagram called the horizontal branch. During this horizontal branch phase, the Sun achieves a new equilibrium somewhat reminiscent of its main sequence days. Core fusion provides a steady energy source. The outward pressure balances gravity's inward pull. The star's size and luminosity are relatively stable. But this stability is temporary, far more temporary than the main sequence phase that preceded it. The problem is that helium burning is far less efficient than hydrogen burning, and the supply of helium fuel in the core is limited. While the Sun spent about 10 billion years fusing hydrogen in its core, it will spend only about 100 million years, roughly 1% as long, fusing helium. In cosmic terms, the horizontal branch phase is a brief interlude between catastrophes. When the core helium is exhausted, the Sun will face another crisis. And this time, the consequences will be even more dramatic. The carbon and oxygen core that remains after helium burning cannot fuse into heavier elements. Carbon fusion requires temperatures of about 500 to 600 million Kelvin, far hotter than even the contracting core of a Sun-like star can achieve. The Sun simply isn't massive enough to generate the crushing gravitational pressures needed to reach such temperatures. So the core contracts again, becoming degenerate again, while helium burning continues in a shell around the carbon-oxygen core. This shell burning dumps more ash onto the core, increasing its mass. Meanwhile, hydrogen burning continues in an outer shell, adding more helium to the helium-burning shell below. The star enters a phase called the asymptotic giant branch, and it expands once more into a red giant configuration. But this time, the expansion is even more extreme. The Sun may grow to 300 times its current radius, extending far beyond the orbit of Mars. Its luminosity will increase to several thousand times its present value. Powerful stellar winds will strip away more and more of its outer layers, feeding material into the surrounding space. The end, now, is truly approaching. As the mass loss accelerates and the shell burning intensifies, the Sun becomes increasingly unstable. Thermal pulses, periodic flashes in the helium-burning shell, cause the star to brighten and dim irregularly. The outer layers, no longer gravitationally bound to the shrinking core, begin to drift away entirely. Within a few 100,000 years, the Sun will shed most of its remaining outer envelope, exposing the hot, dense core to empty space. The ejected material will expand outward, forming a glowing shell of gas illuminated by ultraviolet radiation from the exposed core. This is a planetary nebula, and it represents one of the most beautiful phases in stellar death. The core that remains, stripped of its outer layers, no longer capable of fusion, supported only by electron degeneracy pressure, has become a white dwarf. The Sun's nuclear life is over. All that remains now is a slow, cold descent into darkness that will last for trillions of years. But we're getting ahead of ourselves. The planetary nebula phase and white dwarf formation deserve their own detailed exploration, and they will receive it in the sections to come. For now, let us simply appreciate the remarkable journey we have traced. From a stable, middle-aged star burning hydrogen in its core, through the crisis of hydrogen exhaustion and the onset of shell burning, through the dramatic expansion into a red giant and the explosive ignition of helium fusion, through the brief stability of the horizontal branch and the second expansion of the asymptotic giant branch, the Sun will pass through a series of transformations that would be utterly unrecognizable to observers familiar only with its present state. The physics driving these transformations are the same physics that govern atoms and nuclei here on Earth. The forces involved, gravity, electromagnetism, the strong nuclear force, are the same forces we experience every day. But operating at the scale of a star, over time scales of billions of years, these familiar forces produce outcomes of almost incomprehensible drama and beauty. The sun is going to die, but it will not go quietly. It will blaze brighter than it ever has, expand to swallow planets, shed its outer layers into space, and finally collapse into a dense, glowing ember that will persist for longer than the universe has yet existed. This is the fate of our star. This is the end that awaits the light of our solar system. And in cosmic terms, it is really quite average. Imagine standing on a world that once knew the gentle warmth of a yellow star. For billions of years, life on this world evolved under a sun that rose and set with comforting regularity. Its light neither too harsh nor too dim, its heat neither scorching nor freezing. Generations beyond counting were born, lived, and died under that familiar golden glow. But now, everything has changed. The sun that once appeared as a brilliant white disk, no larger than a fingernail held at arm's length, now dominates the entire sky. It has grown impossibly huge, swelling from a compact sphere into a bloated monster that spans nearly half the heavens. Its color has shifted from cheerful yellow-white to an ominous deep orange-red, as if the entire sky were perpetually caught in the moment of sunset. The horizon is no longer a clean line where sky meets land, but a blur of heat, shimmer, and glare. The air itself thick with the furnace blast of a dying star. This is what the red giant phase looks like from the inside. When the sun exhausts the hydrogen in its core approximately 5 billion years from now and begins shell hydrogen burning, it will embark on a transformation that will take about 1 billion years to complete. At the end of that transformation, the sun will have changed so profoundly that an observer from the present day would barely recognize it as the same star. The expansion begins gradually, almost imperceptibly at first. As the core contracts and shell burning intensifies, the outer layers begin to feel the effects of increased energy output from the interior. This energy pushes outward against the star's own gravity, inflating the envelope like a slowly filling balloon. During the subgiant phase, which lasts perhaps 1 to 2 billion years, the sun will roughly double in radius, while its surface temperature drops from about 5,800 Kelvin to perhaps 5,000 Kelvin. On any surviving inner planet, the changes would be unmistakable. The solar disk would appear larger in the sky. The spectrum of sunlight would shift toward the red end, giving the landscape an unfamiliar tint. Surface temperatures would begin their inexorable climb as the sun's luminosity increased. But these changes, while significant, would be mere preludes to what comes next. Once the sun transitions fully onto the red giant branch, the expansion accelerates dramatically. The numbers involved are staggering. The sun's current radius is approximately 695,700 kilometers. As it ascends the red giant branch, this radius will grow to perhaps 150 million kilometers, over 200 times larger. The sun's current volume is about 1.4 times 10 to the 18th power cubic kilometers. As a red giant, its volume will increase to roughly 10 million times that amount. The density of the outer layers will drop to almost nothing, a gas so thin it would qualify as a decent vacuum by Earth standards, yet still thick enough to exert drag on any object passing through it. At its maximum extent, the edge of the red giant sun will reach approximately to where Earth's orbit lies today. Remember that Earth orbits at about 150 million kilometers, or 1 astronomical unit, AU, from the sun's center. When the sun expands to 200 or more solar radii, Its outer atmosphere will extend to roughly 1 AU from the center, potentially engulfing our planet entirely. But the expansion doesn't happen uniformly or smoothly. The red giant phase is characterized by instability and variability that would make our current sun seem almost boringly constant by comparison. As the hydrogen-burning shell works its way outward through the star's envelope, it encounters regions of varying composition and density. The shell-burning rate fluctuates. The energy output varies. The outer layers respond to these fluctuations by expanding and contracting irregularly. Pulsations and oscillations ripple through the stellar envelope, causing the sun's brightness to vary by factors of 2 or more over periods of months to years. Meanwhile, the core continues its own drama far below. During the red giant phase, the helium core is growing steadily as the shell burning dumps more and more helium ash onto it. The core contracts under its own weight, heating up as gravitational energy is converted to thermal energy. The temperature climbs from tens of millions of Kelvin toward the 100 million Kelvin threshold required for helium ignition. But the core doesn't behave like a normal gas during this compression. As we discussed earlier, the electrons in the core become degenerate, forced into quantum states where they resist further compression, not through thermal pressure, but through the fundamental rules of quantum mechanics. This electron degeneracy pressure halts the gravitational collapse while allowing the temperature to continue rising. The stage is set for the helium flash. When the core temperature finally reaches approximately 100 million Kelvin, helium fusion ignites. But because the core is degenerate, it cannot expand to moderate the reaction. The fusion rate skyrockets in a runaway thermonuclear explosion that releases, for a few brief minutes, more energy than the entire galaxy normally produces. During the helium flash itself, the core temperature may spike to 300 million Kelvin or higher. The energy released is almost beyond comprehension, roughly 100 billion times the sun's current luminosity, compressed into a few minutes of nuclear fury. If this energy were to reach the surface, it would blow the star apart. But it doesn't reach the surface. Instead, the energy is absorbed by the layers above the core, lifting the electron degeneracy and allowing the core to finally expand and cool to a stable helium-burning configuration. An observer on the surface of the red giant, if such an observer could somehow exist in that hellish environment, would notice almost nothing. Perhaps a slight flicker in luminosity, a momentary fluctuation that could easily be attributed to the normal variability of a red giant star. The helium flash, despite its incredible violence, is one of the best hidden events in stellar astrophysics. Once the helium flash has passed and stable helium burning is established in the core, the sun enters a new phase of relative calm, the horizontal branch. The triple alpha process, the fusion of 3 helium nuclei into 1 carbon nucleus, now provides the core's primary energy source. This process releases less energy per reaction than hydrogen fusion, but it's enough to establish a new equilibrium. The outward pressure from core helium burning balances gravity's inward pull. The sun contracts somewhat from its maximum red giant extent, settling into a configuration perhaps 10 to 20 times larger than its present main sequence size. During this phase, the sun's interior consists of several distinct layers, each with its own energy source and behavior. At the center lies the helium-burning core, converting helium into carbon and oxygen through the triple alpha process and subsequent alpha captures. Surrounding this is a thin shell still burning hydrogen into helium, a remnant of the shell burning that dominated the red giant phase. Above this lies the vast hydrogen envelope, the expanded outer layers that give the star its giant appearance. The horizontal branch phase is relatively brief. While the main sequence lasted some 10 billion years, and even the red giant branch lasts perhaps 1 billion years, the horizontal branch is measured in hundreds of millions of years, perhaps 100 to 200 million years for a sun-like star. The reason is simple. Helium burning is less efficient than hydrogen burning, and the helium supply in the core is limited. Once it's gone, another crisis ensues. When the core helium is exhausted, the sun faces a familiar problem. No more fuel in the core, nothing to generate the outward pressure needed to resist gravitational collapse. The core, now composed primarily of carbon and oxygen, begins to contract again. Degeneracy pressure again comes into play, halting the collapse before the core is crushed into a neutron star. Meanwhile, helium burning ignites in a shell around the carbon-oxygen core, just as hydrogen burning continues in a shell above that. The sun now has 2 burning shells, a helium shell and a hydrogen shell, feeding energy into the outer envelope. This marks the beginning of the asymptotic giant branch phase, and it represents the final act of the sun's life as a fusion-powered star. On the asymptotic giant branch, the sun will expand once more, even larger than during its first red giant phase. Some models suggest it could reach 300 or more times its current radius, extending well past the current orbit of Mars. Its luminosity will increase to thousands of times its present value. The outer layers will become increasingly loosely bound to the core, held on by only the feeblest gravitational attraction. The asymptotic giant branch is also characterized by dramatic instability. The dual shell-burning structure creates complex feedback loops and thermal pulses that cause the star's luminosity to fluctuate wildly. Every 10,000 to 100,000 years, the helium-burning shell experiences a brief burst of intense fusion, a thermal pulse that temporarily boosts the star's luminosity and drives convective mixing through the envelope. These thermal pulses have profound consequences for the chemistry of the star. During each pulse, convection can dredge up material from the deep interior, including carbon freshly synthesized by the triple alpha process, and mix it into the outer envelope. This process, called dredge-up, enriches the surface layers with carbon and other heavy elements that will eventually be expelled into space. The stellar wind also intensifies dramatically during the asymptotic giant branch phase. Particles streaming from the sun's surface carry away mass at rates perhaps 1 million times greater than the current solar wind. Over the course of the asymptotic giant branch evolution, the sun will lose roughly 40 to 50% of its original mass, expelled into the surrounding space to form a slowly expanding shell of gas and dust. This mass loss has important consequences for the inner solar system. As the sun loses mass, its gravitational grip on the planets weakens. The planet's orbits expand outward in response, migrating to larger distances from the shrinking stellar core. By the end of the asymptotic giant branch phase, Earth, if it survives, will orbit perhaps 1.5 to 2 AU from the sun, rather than its present 1 AU. But survival is far from guaranteed. Throughout the red giant and asymptotic giant branch phases, Earth faces multiple threats to its existence. The intense radiation from the bloated sun will have long since vaporized the oceans and stripped away the atmosphere. The surface temperature will exceed 2,000 degrees Celsius, hot enough to melt most rocks. Any traces of life that once existed will have been sterilized billions of years before the asymptotic giant branch phase even begins. The question is whether Earth will survive as a physical object, whether it will maintain its structural integrity as a planet, or be completely destroyed. If Earth's orbit expands fast enough to stay ahead of the swelling sun, The planet may persist as a scorched, airless husk orbiting the remnant stellar core. But if the orbit doesn't expand quickly enough, Earth could be engulfed by the outer atmosphere of the red giant. In that case, drag from the tenuous but extensive gas envelope would cause Earth to spiral inward, falling ever deeper into the dying star until it is completely vaporized. Mercury and Venus face no such uncertainty. They will definitely be consumed. Mercury, orbiting at just 0.39 AU, has no hope of escaping the Sun's expansion to 1 AU or beyond. Venus, at 0.72 AU, is similarly doomed. Both planets will be swallowed, spiral inward, and ultimately vaporize within the stellar envelope. Mars, at 152 AU, is probably safe from engulfment. The Sun's expansion is unlikely to reach Mars's orbital distance, especially after accounting for orbital expansion due to solar mass loss. Mars will survive the red giant phase as an irradiated but intact planet, though any remnants of the rover missions we've sent there will long since have melted into slag. The outer planets, Jupiter, Saturn, Uranus, Neptune, will survive relatively unscathed. They're simply too far away to be directly affected by the Sun's expansion. Jupiter orbits at 5.2 AU, Saturn at 9.5 AU, Uranus at 19.2 AU, and Neptune at 30.1 AU. Even the most extreme estimates of red giant expansion don't reach anywhere near these distances. The gas giants will watch their parent star die from a safe remove, their moons potentially becoming warmer and more hospitable as the Sun's luminosity temporarily increases. But even for the surviving planets, nothing will ever be the same. The Sun they once knew, stable, reliable, comforting, will have transformed into something monstrous and temporary. The red giant phase is not an ending in itself, but a transition, a passage between what the Sun was and what it will become. That final transformation, the shedding of the outer envelope and the exposure of the stellar core, is what we will explore next. The planetary nebula awaits, and with it, the birth of a white dwarf that will shine ever more faintly for trillions of years to come. The death of a star, it turns out, is a drawn-out affair. It takes billions of years for the fuel to run out, millions more for the red giant phase to play out, thousands more for the stellar envelope to be expelled. And even then, the stellar remnant persists, not alive in any meaningful sense, but not truly dead either, slowly cooling in the cosmic darkness for timescales that dwarf everything that came before. This is the fate of our Sun. This is how stars like ours end their days, not in a single cataclysmic explosion, but in a long, spectacular sunset that paints the cosmos in hues of red and gold before fading, at last, to black. As the Sun approaches the end of its asymptotic giant branch phase, it becomes a star in crisis, unstable, pulsating, shedding mass at an accelerating rate. The stellar wind that once carried away mere wisps of material has become a gale, stripping thousands of Earth masses worth of gas from the dying star every million years. The outer envelope, once firmly bound by gravity, has become increasingly tenuous, held on by only the feeblest attraction to the shrinking core below. And then, over a cosmically brief span of perhaps 100,000 years, that envelope lets go entirely. The process is not a violent explosion, but more like an exhale, the final breath of a dying giant released into the surrounding space. The outer layers, no longer gravitationally bound to the core, drift outward at velocities of 20 to 30 kilometers per second. This might seem slow compared to stellar explosions, but it's fast enough to carry the ejected material far from the shrinking stellar remnant. What remains behind is the exposed core of the former star, a sphere of carbon and oxygen roughly the size of Earth, but containing roughly half the mass of the Sun. No fusion reactions occur within it. No new energy is being generated. It is supported against gravitational collapse solely by the quantum mechanical pressure of degenerate electrons, packed so tightly that the laws of physics forbid them from being squeezed any closer together. This object is a white dwarf, and its emergence marks the end of the sun's nuclear life. But before we examine the white dwarf itself, let us pause to appreciate the spectacular phenomenon created by its birth: the planetary nebula. The name planetary nebula is one of the great misnomers in astronomy. These objects have nothing whatsoever to do with planets. The name dates back to the 18th century, when astronomer William Herschel observed these fuzzy, disc-shaped objects through his telescope and thought they resembled the distant planets Uranus and Neptune. The name stuck. Even as astronomers came to understand that planetary nebulae were something far more exotic than planets, they were the cast-off outer layers of dying stars. When the sun's outer envelope drifts away into space, it doesn't simply disperse and disappear. The newly exposed white dwarf at the center is extraordinarily hot. Surface temperatures can exceed 100,000 Kelvin, far hotter than the sun's present surface temperature of about 5,800 Kelvin. At these temperatures, the white dwarf emits intense ultraviolet radiation, photons so energetic they can strip electrons from atoms in the surrounding gas. This process, called photoionization, transforms the expanding shell of gas into a glowing emission nebula. The ionized atoms eventually recapture electrons, and as they do, they emit photons at characteristic wavelengths determined by the atomic species involved. Hydrogen atoms glow red. Oxygen atoms produce vivid greens and blues. Nitrogen contributes deep reds and purples. The result is a cosmic light show of extraordinary beauty, a glowing shell of multicolored gas surrounding a tiny, intensely hot stellar remnant. Planetary nebulae are among the most visually stunning objects in the universe. The Hubble Space Telescope has captured images of hundreds of them, revealing an astonishing diversity of shapes and structures. Some are nearly perfect spheres, smooth and symmetric. Others are elongated into hourglass shapes or butterfly patterns, their forms sculpted by magnetic fields, stellar rotation, or companion stars. Still others display complex internal structures, knots and filaments, jets and bubbles that speak to the tumultuous processes occurring as the dying star sheds its outer layers. The Ring Nebula in the constellation. Lyra is perhaps the most famous example. Through even a modest telescope, it appears as a small, smoke ring-shaped object with a faint star at its center. That faint star is the white dwarf remnant, and the ring is the ejected envelope, still glowing from the ultraviolet radiation pouring out of the stellar core. The Helix Nebula, one of the closest planetary nebulae to Earth at about 700 light-years away, is large enough to span nearly half the apparent diameter of the full moon in our sky, though it's too faint to see without a telescope. High-resolution images reveal a complex structure of comet-shaped knots streaming away from the central star. Each knot a dense clump of gas being photoevaporated by the intense radiation. The Cat's Eye Nebula displays intricate concentric shells and jets, evidence of episodic mass ejection events, and possibly the influence of a binary companion star. The Butterfly Nebula, NGC 6302, showcases extreme bipolar symmetry, its twin lobes expanding away from a central star hidden behind a dense disk of dust. When our sun creates its planetary nebula approximately 5 billion years from now, what will it look like? That's difficult to predict with certainty. The shape and structure of a planetary nebula depend on factors we can't easily determine in advance: the exact rate and timing of mass loss, the influence of any magnetic fields, the possible presence of surviving planets or companion objects that might shape the outflow. The Sun's planetary nebula might be a smooth sphere, or it might display the complex asymmetries seen in so many other nebulae. What we can predict is that it won't last long. Planetary nebulae are transient phenomena on cosmic timescales. The expanding shell of gas continues to spread outward, becoming thinner and more diffuse with each passing millennium. Meanwhile, the white dwarf at the center is cooling, its ultraviolet output declining. Within perhaps 20,000 to 50,000 years, a blink of an eye compared to the billions of years of stellar evolution that preceded it, the nebula will have faded into invisibility, dispersed into the interstellar medium from which future generations of stars will someday form. The atoms that once made up the Sun's outer layers, hydrogen, helium, carbon, nitrogen, oxygen, and traces of heavier elements, will drift through space for millions or billions of years. Eventually, they will be swept up by the gravitational attraction of a giant molecular cloud, mixed with material from other dead stars, and compressed into a new generation of stellar nurseries. The carbon atoms fused in our Sun's core during its red giant phase might one day form the backbone of organic molecules on a planet we cannot imagine, orbiting a star that does not yet exist. This is the great cycle of stellar recycling, the cosmic process by which dead stars give birth to new ones. Our own solar system formed from material processed through previous generations of stars. The oxygen we breathe, the carbon in our bodies, the iron in our blood, all were forged in stellar cores and scattered into space by stellar deaths. We are, quite literally, made of star stuff. But let us return to the white dwarf, that dense stellar ember left behind when the planetary nebula fades. A white dwarf is one of the strangest objects in the known universe, not as exotic as a neutron star or black hole perhaps, but bizarre enough in its own right. Imagine taking the mass of the Sun, or at least half of it, since the other half was expelled in the planetary nebula, and compressing it into a sphere the size of Earth. The result is a density almost impossible to comprehend, about 1 million grams per cubic centimeter, roughly 200,000 times denser than Earth, and about 1 million times denser than water. At such densities, a teaspoon of white dwarf material would weigh about 5.5 metric tons. A sugar cube's worth would be as heavy as a car. The entire mass of the Moon, compressed to white dwarf density, would fit inside a sphere about 100 meters across. This extreme density is possible only because of the quantum mechanical properties of electrons. Under normal circumstances, matter resists compression because the electrons surrounding atomic nuclei repel each other. But when matter is compressed to white dwarf densities, those electrons are stripped from their atoms and form a degenerate gas, a sea of electrons packed so tightly that quantum mechanics takes over. The Pauli exclusion principle states that no two identical fermions, a category that includes electrons, can occupy the same quantum state. In a degenerate gas, the electrons have been compressed to the point where they occupy the lowest available energy states. Any further compression would require forcing electrons into already occupied states, which the laws of physics simply don't permit. The result is degeneracy pressure, an outward force that has nothing to do with temperature, and everything to do with the fundamental nature of quantum mechanics. This degeneracy pressure is what supports a white dwarf against gravitational collapse. Unlike a main sequence star, which is supported by thermal pressure generated by nuclear fusion, a white dwarf is supported by a pressure that would exist even at absolute zero temperature. The white dwarf doesn't need fusion to survive. It just needs electrons. There is, however, a limit to how much mass electron degeneracy pressure can support. This limit, calculated by astrophysicist Subramanian Chandrasekhar in 1930, is approximately 1.4 solar masses, known appropriately as the Chandrasekhar limit. If a white dwarf were to exceed this mass, electron degeneracy pressure would be overwhelmed by gravity, and the star would collapse further, potentially into a neutron star or black hole. For the Sun, this limit is not a concern. The Sun will lose roughly half its mass during the red giant and asymptotic giant branch phases, leaving behind a white dwarf of about 0.5 to 0.6 solar masses, well below the Chandrasekhar limit. Our white dwarf remnant will be stable, supported by electron degeneracy pressure, for essentially the rest of time. But stable does not mean unchanging. Although no fusion occurs within a white dwarf, the object is far from static. When first exposed by the dispersal of the planetary nebula, a white dwarf is extraordinarily hot. Surface temperatures can exceed 100,000 Kelvin, making it blue-white in color and intensely luminous in the ultraviolet. This heat is residual, left over from the star's previous life. The white dwarf has no way to generate new heat. It can only radiate away what it already has. And radiate it does. Energy streams away from the white dwarf's surface into the cold void of space, carrying away heat that will never be replaced. The white dwarf cools, its surface temperature dropping, its luminosity fading. What was once blue-white shifts to white, then to yellow, then to orange, then to red, as the temperature drops through thousands of Kelvin over billions of years. The cooling process is governed by relatively simple physics. The white dwarf radiates energy at a rate proportional to its surface area and the fourth power of its temperature, but the timescales involved are almost beyond comprehension. After about 1 billion years, a typical white dwarf will have cooled to perhaps 10,000 Kelvin, still hot by terrestrial standards, but no longer the incandescent furnace it once was. After 4 billion years, it might reach 5,000 to 6,000 Kelvin, roughly the surface temperature of the present-day Sun, though packed into a sphere the size of Earth. After 10 billion years, it could be down to 3,000 to 4,000 Kelvin, a dim red ember barely visible against the background stars. But the cooling doesn't stop there. After 15 or 20 billion years, longer than the current age of the universe, the white dwarf will have cooled to perhaps 2,000 Kelvin, radiating primarily in the infrared rather than visible light. After 100 billion years, it might reach 500 Kelvin, still warm enough to be detected by sensitive instruments, but essentially invisible to the naked eye. And eventually, after trillions of years, the white dwarf will approach a temperature near absolute zero, radiating away the last vestiges of its residual heat until it reaches thermal equilibrium with the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space at a temperature of about 2.7 Kelvin. At this point, the white dwarf will have become something new: a black dwarf. A black dwarf is the theoretical final state of a white dwarf that has cooled completely, a sphere of degenerate carbon and oxygen at the temperature of the cosmic void, emitting essentially no radiation, invisible to any conceivable telescope. It is the ultimate endpoint of stellar evolution for stars like our Sun. Not a violent explosion, not a gravitational collapse into a black hole, but a slow, quiet fade into darkness that takes longer than the current age of the universe to complete. No black dwarfs currently exist. The universe is only about 13.8 billion years old, and even the oldest white dwarfs, formed from stars that died billions of years ago, have not had enough time to cool significantly. The coolest known white dwarfs still have surface temperatures of several thousand Kelvin, far too warm to qualify as black dwarfs. It will be at least another 10 to 15 billion years before the first black dwarfs begin to form, and trillions of years before they become common. But eventually, if the universe continues to expand and cool as current cosmological models predict, black dwarfs will be among the most common stellar remnants in existence. Long after the last stars have burned out, long after the last red dwarfs have exhausted their hydrogen fuel, countless black dwarfs will drift through the cosmos, silent, dark, cold, carrying within their degenerate cores the processed remains of stars that shone billions or trillions of years before. This is the fate that awaits our sun. 5 billion years from now, give or take, it will shed its outer layers and expose its white dwarf core. That core will cool for billions of years, fading from brilliant white to dull red to invisible black, and then, for trillions upon trillions of years, it will persist as a black dwarf, a frozen monument to the star that once warmed our planet and made life possible. It's a melancholy fate in some ways, this slow descent into eternal darkness. The sun that gave us life will eventually become a cold, dead cinder drifting through the void. But there's also something strangely beautiful about it. The sun's matter won't be destroyed. It will persist, locked in the crystalline lattice of a degenerate carbon-oxygen sphere, essentially forever. Long after every galaxy has fallen silent, long after the last photon of starlight has faded into the cosmic background, the atoms that once made up our sun will still exist, still bound together by forces that have operated since the first moments after the Big Bang. And who knows, perhaps, in some impossibly distant future, those atoms will find new purpose. Perhaps the black dwarf that was once our sun will drift into a region where new forms of matter or energy operate under rules we cannot imagine. Perhaps it will witness the final fate of the universe itself, whatever that might be. The death of a star is not really an ending. It's a transformation, a transition from one state of being to another. The sun will die, yes, but its matter will endure, changed, cooled, darkened, but not destroyed. In the grand scheme of the cosmos, that's as close to immortality as anything can hope to achieve. Let us now enter the realm of the impossible. Everything we have discussed so far, the red giant phase, the helium flash, the planetary nebula, the white dwarf, represents the actual future of our sun, predicted by well-established physics and confirmed by observations of countless other stars at various stages of their evolution. That future is billions of years away, and while it will eventually transform our solar system beyond recognition, it will unfold slowly enough that any sufficiently advanced civilization would have ample time to adapt or relocate. But what if we stripped away that luxury of time? What if, instead of the slow, majestic death that awaits our star, we imagined something far more sudden and far more terrifying? What if the sun simply vanished? Now, let me be absolutely clear. This is not going to happen. The sun cannot simply disappear. Matter and energy do not vanish from the universe. This is one of the most fundamental laws of physics, tested and verified countless times in laboratories and observations around the world. The sun contains roughly 2 nonillion kilograms of matter, and that matter has to go somewhere. It cannot simply cease to exist. Could matter quantum tunnel to a different location? Theoretically, yes. Quantum mechanics allows for particles to spontaneously appear in locations they shouldn't be able to reach through classical means. but the probability of an object the size of an atom quantum tunneling even a short distance is vanishingly small. The probability of an object containing roughly 10 to the 57th power atoms, the approximate number of atoms in the Sun, simultaneously quantum tunneling to the same distant location is so absurdly improbable that there isn't enough time in the lifetime of millions upon millions of universes for such an event to occur even once. So why discuss it at all? Because this impossible scenario serves as a powerful thought experiment, a way to understand just how dependent Earth and everything on it truly is upon our parent star. By imagining what would happen if the Sun vanished instantaneously, we can appreciate the countless ways solar energy sustains our world, from the obvious, light and heat, to the subtle, gravitational stability and the water cycle. We can explore the resilience of life and the limits of human survival in ways that illuminate truths about our planet and our place in the cosmos. So let us set aside the laws of conservation for a moment and imagine the unimaginable. Let us explore what would happen to Earth if, at some arbitrary moment, the Sun simply winked out of existence. The first thing to understand is that we wouldn't know immediately. The Sun sits approximately 150 million kilometers from Earth, a distance so vast that light, traveling at roughly 300,000 kilometers per second, takes 8 minutes and 20 seconds to cross it. This means that the sunlight warming your skin right now actually left the Sun's surface over 8 minutes ago. You are not seeing the Sun as it is. You are seeing the Sun as it was 8 minutes and 20 seconds in the past. If the Sun were to vanish at this very instant, we would have no idea for the next 8 minutes and 20 seconds. The sky would remain bright, the temperature would remain comfortable, birds would continue singing, children would continue playing, and the world would carry on in blissful ignorance of the catastrophe that had already occurred. For those 500 seconds, everything would seem perfectly normal, even though the source of all that normalcy had already ceased to exist. And then, without warning, the sky would go dark. Not the gradual darkness of sunset, where the light slowly fades from gold to orange to deep blue to black. This would be instantaneous. One moment, bright daylight, the next moment, utter blackness. On the day side of Earth, billions of people would watch the Sun simply switch off. As if someone had flipped a cosmic light switch, the blue sky would vanish, replaced by the star-filled blackness of space. The temperature, still warm from the accumulated heat of the day, would begin its long, inexorable decline. But the disappearance of light would not be the only consequence of the Sun's vanishing act. Gravity, like light, propagates at a finite speed, specifically at the speed of light. This was one of Einstein's key insights. Changes in gravitational fields cannot travel faster than approximately 300,000 kilometers per second. If a massive object suddenly changes position or ceases to exist, the gravitational effects of that change ripple outward at the speed of light, reaching distant objects only after a delay proportional to their distance. This means that at the exact moment we saw the Sun disappear from our sky, we would also lose its gravitational influence. For 8 minutes and 20 seconds after the Sun vanished, Earth would continue orbiting normally, held in its path by a gravitational field that no longer had a source. And then, at the precise instant the darkness arrived, that gravitational tether would snap. What would happen next is a simple matter of physics. An object in circular motion has velocity directed tangent to its path, perpendicular to the line connecting it to the center of its orbit. When you swing a ball on a string in a circle and then release the string, the ball doesn't fly toward or away from your hand. It flies off in a straight line tangent to the circle at the point of release. Earth would do exactly the same thing. At the moment the Sun's gravity ceased to reach us, Earth would be moving at approximately 30 kilometers per second, its normal orbital velocity. Without the sun's gravity to bend that motion into a curve, Earth would simply continue in a straight line at that speed, heading off into the interstellar void. We wouldn't feel this sudden change in trajectory. There would be no jolt, no sensation of acceleration, because Earth's orbital motion is already carrying us at that speed. We would simply stop curving and start flying straight. The moon, bound to Earth by our planet's gravity rather than the sun's, would come with us. Our faithful companion would continue its monthly dance around our planet as we both hurtled into the darkness. The tides would still rise and fall, though there would soon be no liquid oceans left to feel them. Now, here is where things become truly strange. The finite speed of light and gravity means that as panic and fear spread across Earth, we could still look up into the sky and see our planetary companions continuing to behave as if nothing had happened. Jupiter, orbiting at roughly 780 million kilometers from the Sun, would continue reflecting sunlight for about 43 minutes after Earth knew the Sun was gone. We would watch the gas giant sailing serenely across the suddenly starry sky, illuminated by a sun that had already ceased to exist, orbiting a gravitational center that had already vanished. And depending on where Jupiter was in its orbit relative to Earth, it would take another 35 to 50 minutes for that reflected light to reach us after Jupiter itself went dark. We might watch Jupiter for over an hour after the sun's disappearance, a ghostly reminder of the solar system that once was. Saturn, even farther out at approximately 1.4 billion kilometers from the Sun, would continue its illuminated orbit for about 80 minutes after the Sun vanished. Uranus and Neptune, the ice giants of the outer solar system, would keep up their sunlit appearances for hours. Observers on Earth, if any remained calm enough to watch the sky, could track the progressive extinction of reflected light across the solar system, watching darkness claim each planet in turn as the light-time delay caught up with them. The psychological impact of this scenario is almost impossible to overstate. Human beings have evolved under a sun that rises and sets with clockwork regularity. Our circadian rhythms, our agricultural practices, our religious traditions, our very conception of time itself, all are built around the daily cycle of light and darkness, the annual cycle of seasons, the fundamental reliability of solar radiation. The sun has been a constant presence in human experience since before there were humans to experience it. Our hominid ancestors watched it rise over the African savanna. Our ancient civilizations worshipped it as a god. Every culture on Earth has stories and myths centered on the sun's life-giving power. To have that presence suddenly and inexplicably vanish would be a trauma beyond anything in human history. The psychological shock alone might be enough to end civilization, even before the physical consequences began to take their toll. Mass panic, religious hysteria, complete social breakdown, all would likely occur within hours or days of the sun's disappearance. The careful structures of society, built up over millennia, might crumble almost instantly in the face of this ultimate cosmic abandonment. Confusion would reign supreme in those first moments. What had happened? Was this real? Could the sun possibly have just stopped existing? People would flood onto the streets, staring upward at an impossibly dark daytime sky, seeing stars where moments before there had been blue heavens. The initial assumption might be some sort of eclipse, but eclipses don't work like this. They're gradual, predictable, and they end. This darkness would be sudden, total, and permanent. Communication systems would likely survive for a while, allowing people around the world to share their terror and confusion. Those on the night side of Earth would notice the stars behaving strangely, familiar constellations shifting subtly as Earth's trajectory changed from orbital curve to straight line. Astronomers, if they could overcome their shock, might be the first to understand what had happened, calculating from the sudden changes in stellar positions that Earth was no longer following its accustomed path. But understanding would bring no comfort. Knowing that you're about to freeze to death in the cosmic void is not meaningfully better than not knowing. Meanwhile, the other objects in the solar system would begin their own journeys into darkness. Mercury and Venus, closer to the Sun than Earth, would receive the news of the Sun's disappearance before we did. Mars, farther out, would learn roughly 12 minutes after Earth. Each planet would fly off on its own tangent, the carefully orchestrated dance of the solar system dissolving into 8 separate trajectories, heading off in 8 different directions. The asteroids of the asteroid belt, the icy bodies of the Kuiper belt, the countless comets of the Oort cloud, all would be released from the Sun's gravitational grip, each following its own path into the interstellar medium. The solar system, that intricate mechanism that has operated for 4.6 billion years, would simply cease to exist as a coherent structure. What had been a family of worlds would become a diaspora, each member heading off alone into the infinite darkness. Within hours, the reality of the situation would become undeniable. Temperatures would begin dropping perceptibly. The last light of the vanished sun would fade from the sky. Humanity would face the stark choice that all doomed creatures eventually face: fight, flee, or accept the inevitable. There would be nowhere to flee. And so the fight would begin, a desperate, doomed struggle against the inexorable cooling of a planet suddenly cast adrift from its parent star. Some would give up immediately, succumbing to despair or choosing to end things on their own terms. Others would rage against the dying of the light, determined to survive as long as possible by whatever means necessary. But survival, as we shall see, would be far more difficult than anyone might imagine. The Earth we know, the green and blue and white world teeming with life, would soon begin a transformation into something cold, dark, and utterly alien. The descent into darkness had begun. In those final hours before the cold became unbearable, people around the world would respond in characteristically human ways. Some would gather with loved ones, holding each other close as the temperature dropped, finding comfort in human connection, even as everything else fell apart. Others would turn to religion, seeking meaning and solace in faith traditions that suddenly seemed more urgent than ever. Still others would rage against the dying of the light, launching futile scientific efforts to somehow bring the sun back or find an explanation for its impossible disappearance. There would be those who simply couldn't accept what had happened, who would convince themselves that this was a dream or a temporary phenomenon or some kind of elaborate deception. Denial is a powerful psychological defense mechanism, and in the face of something this incomprehensible, many minds would simply refuse to process the reality. They would wake up each morning expecting to see the sun restored, only to confront the same star-filled darkness they had gone to sleep under. The infrastructure of civilization would begin failing almost immediately. Power grids, designed to handle predictable patterns of demand, would be overwhelmed as everyone tried to heat their homes simultaneously. Transportation systems would grind to a halt as temperatures dropped below the operating limits of vehicles and fuel lines. Communication networks would persist longer. Radio waves don't care about temperature, but the towers and satellites that relay those signals would eventually succumb to the cold or loss of power. And through it all, the silent testimony of the outer planets would continue. That eerie sight, Jupiter still shining, Saturn still gleaming, the reflected light of a vanished sun still bouncing off distant worlds, would be one of the most psychologically disturbing aspects of the entire catastrophe. It would be a constant reminder that the universe had changed irrevocably, that the familiar order of things had been shattered, that humanity was now utterly alone in a cosmos that no longer made sense. The outer planets would wink out one by one, their reflected light finally exhausting as the last photons from the vanished sun completed their journeys. First Jupiter, then Saturn, then the barely visible points of Uranus and Neptune, and then, truly, it would be over. The solar system as we knew it would be gone, its components scattered to the cosmic winds, its central fire extinguished. Its billions of years of history concluded in a single impossible instant. Only then, perhaps, would the full weight of what had happened begin to sink in. Only then would humanity truly understand that the sun, that reliable, eternal, life-giving presence, was never coming back. The descent into darkness had begun. The moment the sun's light stops reaching Earth, a countdown begins. Not a countdown to a single catastrophic event, but to a cascading series of failures that will systematically dismantle every system on which life depends. The warmth we take for granted, the air we breathe, the water we drink, the food we eat, all of these are downstream consequences of solar energy, and all of them will begin to fail the instant that energy stops arriving. Let us follow that countdown, step by step, into the frozen darkness that awaits. The first and most immediate casualty is photosynthesis. This biochemical process, which has been converting solar energy into chemical energy for roughly 3.5 billion years, would halt the instant the sun's light stopped reaching Earth's surface. Every green plant, every algae cell, every cyanobacterium would suddenly find itself unable to perform the fundamental reaction that sustains it, capturing photons of light and using their energy to combine carbon dioxide and water into glucose and oxygen. The scale of this shutdown is difficult to comprehend. Approximately 99.9% of all natural productivity on Earth is driven by photosynthesis. Nearly every ecosystem on the planet's surface depends, directly or indirectly, on the ability of photosynthetic organisms to capture solar energy and make it available to the rest of the food web. Take away that foundation, and the entire structure begins to collapse. But the collapse would not be immediate, at least, not the collapse caused by oxygen depletion. Collectively, all 8 billion or so human beings on Earth breathe in approximately 6 trillion kilograms of oxygen every year. Add in all the other oxygen-breathing organisms, animals, insects, fungi, aerobic bacteria, and the total consumption rises significantly. But Earth's atmosphere contains a staggering quintillion kilograms of oxygen. Even with photosynthesis completely shut down, even with all oxygen-breathing life continuing to respire normally, it would take thousands of years to deplete that atmospheric reservoir. So, we would not suffocate. Not quickly, anyway. The plants themselves would be far worse off. Without sunlight, they cannot produce the glucose they need for energy. Most small plants would die within days or weeks, their cellular processes grinding to a halt as their energy reserves ran out. Larger plants, particularly trees with massive trunks containing stored sugars, could potentially survive for years, drawing on their reserves to maintain basic metabolism. But they would never get the chance to starve to death. The cold would claim them first. Let us talk about temperature. Right now, with our sun shining reliably in the sky, the average surface temperature of Earth, taking into account hot places and cold places, summer and winter, day and night, is approximately 14 to 15 degrees Celsius. or about 57 to 59 degrees Fahrenheit. This is remarkably comfortable by cosmic standards, hovering in the narrow range that allows liquid water to exist and complex chemistry to proceed. This temperature is not Earth's natural state. Without the sun, our planet would be far, far colder. The only reason Earth is warm enough to support life is that solar radiation constantly bathes our planet, adding energy faster than the planet radiates it away into space. Remove that input, and the equation changes dramatically. Heat loss from a warm body into a cold environment follows an exponential curve, fast at first, then slower as the temperature differential decreases. In the hours immediately after the sun's disappearance, Earth would begin radiating heat into space at a prodigious rate. The atmosphere, no longer being warmed by incoming sunlight, would begin cooling almost immediately. By the end of the first week without the sun, the average global surface temperature would drop to approximately 0 degrees Celsius, freezing point. This might not sound catastrophic. After all, temperatures like this occur regularly in winter across much of the planet. People are used to cold weather. Heating systems exist. Life can continue. But remember, this is the average temperature, and it's getting colder by the day. The coldest regions of Earth would already be experiencing temperatures far below anything in modern human experience. And there would be no relief coming, no spring to look forward to, no warm front moving in, no promise that things would ever get better. The cold would creep across the planet like a slow-motion tide of death. In the first few months, the most immediate human crises would be energy and food. Power plants would still function: coal, natural gas, nuclear, hydroelectric. But the infrastructure that supports them would begin to strain under unprecedented demand. Everyone, everywhere, would be cranking up their heating systems simultaneously. Fuel reserves that were expected to last months or years would be depleted in weeks. Food production would collapse almost immediately. Modern agriculture depends absolutely on solar energy, not just for photosynthesis in crops, but for the warmth that allows growing seasons to exist. In a world where the temperature is dropping toward negative 73 degrees Celsius, no crops can grow. Livestock cannot survive in open pastures. The entire agricultural system that feeds 8 billion people would simply cease to function. By the end of the first year without the sun, the average global surface temperature would plummet to approximately negative 73 degrees Celsius, about negative 100 degrees Fahrenheit. For reference, the coldest temperature ever recorded on Earth was negative 89.2 degrees Celsius, measured at the Soviet Vostok Station in Antarctica in July 1983. Within a year of the sun's disappearance, such temperatures would be normal across most of the planet's surface. The tropics would be as cold as Antarctica is today. Antarctica would be cold beyond anything in human experience. At these temperatures, human survival outdoors is simply impossible. Exposed flesh freezes within minutes. Breath crystallizes in the air. Metal becomes so cold, it burns skin on contact. Any human beings remaining on the surface would be dead, frozen solid. Their bodies preserved in the deepening cold like specimens in some cosmic museum. The water cycle, that elegant system by which the sun's energy evaporates water from the oceans, lifts it into the atmosphere, and deposits it as rain and snow across the continents, would cease entirely. Without solar energy to evaporate water, clouds cannot form. Without clouds, there is no precipitation. Rivers would stop flowing as their sources dried up. Groundwater would freeze in the soil. The polar ice caps, currently held in check by the balance between snowfall and melting, would begin their relentless expansion. Ice would spread from the poles toward the equator, kilometer by kilometer, year by year. The white surface of the ice would reflect whatever starlight reached the planet, but there would be precious little light to reflect. Eventually, the expanding polar ice caps would meet at the equator. The oceans would freeze over completely on their surfaces, a shell of ice sealing the liquid water below. But here, paradoxically, is a small mercy. Ice floats. The ice that forms on the ocean surface is less dense than the liquid water beneath it, which means the ice stays on top rather than sinking. And ice, as it happens, is a reasonably good insulator. The ice layer would thicken over time, growing from the surface downward as heat leaked out of the ocean and into space. But it would thicken slowly, because each layer of ice makes it harder for the next layer to form. The water beneath would be protected from the cosmic cold by miles of frozen insulation above, but even protected water faces threats. As more and more water freezes out of the ocean, the concentration of dissolved salts in the remaining liquid increases. The deep oceans would become increasingly saline, so salty that most marine life would be poisoned by the very water it swam in. Fish, mollusks, crustaceans, marine mammals, all the creatures of the sea that we know and love would die off, their corpses sinking to the seafloor in a slow rain of organic matter. Back on the surface, stranger things would begin to happen. In the decades following the sun's disappearance, temperatures would continue dropping, passing -100, then -150, then -200 degrees Celsius. By the time Earth reached the orbit of Pluto in its hypothetical ejection scenario, surface temperatures would hover around -230 degrees Celsius, barely 40 degrees above absolute zero. At these temperatures, the atmosphere itself begins to change state. The air we breathe is composed primarily of nitrogen, about 78%, and oxygen, about 21%, with trace amounts of argon, carbon dioxide, and other gases. Under normal conditions, these gases remain gaseous at all temperatures found on Earth's surface. But at -195 degrees Celsius, nitrogen liquefies. At -218 degrees Celsius, it freezes solid. Oxygen liquefies at -183 degrees Celsius and freezes at -218 degrees Celsius. As Earth's surface temperature drops below these thresholds, a bizarre and terrible spectacle would unfold, though there would be no one left alive to witness it. First, nitrogen would begin to condense out of the atmosphere, forming a thin mist of liquid nitrogen droplets that would settle on every surface. As temperatures continued dropping, that liquid nitrogen would freeze into solid nitrogen frost, coating the rocks, the ice, the frozen corpses of every plant and animal that ever lived on the surface. Then oxygen would follow the same path, condensing from gas to liquid, then freezing from liquid to solid. The air itself would fall as snow. Over a period of years or decades, Earth's atmosphere would be deposited on the surface as a layer of frozen gas perhaps 10 meters thick. The sky would become almost completely empty, not the black of a cloudy night, but the absolute blackness of airless space. Stars would shine down on a world wrapped in frozen air, their light undimmed by any atmosphere. Only a thin whisper of gas would remain, the trace gases with even lower freezing points, too sparse to contribute meaningfully to atmospheric pressure. For all practical purposes, Earth would have become an airless world, its former atmosphere lying in frozen drifts across a landscape of ice and rock. The frozen remains of Earth's biosphere would lie preserved beneath this blanket of crystallized air. Forests, cities, coral reefs, prairies, everything that once lived on the surface would be entombed in ice and nitrogen snow, flash frozen and preserved for eternity. The bodies of every creature that failed to escape underground would become permanent residents of this frozen museum, their forms unchanged by decay in a world too cold for decomposition. Earth would no longer be the pale blue dot we know from photographs taken by distant spacecraft. It would be a pale gray-white marble, an icy tomb drifting through the darkness, carrying the frozen echoes of 4 billion years of evolution into the infinite void. This would be the fate of our planet's surface if the sun disappeared. But as we shall see, even in this frozen nightmare, there would be survivors. Not on the surface. Nothing could survive there. But deep below, in places the sun's warmth never reached even when it was shining, life would continue. And in carefully prepared refuges, some humans might manage to survive as well, at least for a while. The surface might be lost, but Earth's story would not be over. Not quite yet. What would this frozen Earth look like? Could anyone observe it from space? The transformation would be complete and profound. Where once a blue and white marble hung in the cosmic void, oceans reflecting sunlight, clouds swirling in delicate patterns, green continents visible through the atmosphere, there would now be something utterly alien. A gray-white sphere, featureless and cold, wrapped in a layer of frozen atmospheric gases. No weather would disturb its surface. No seasons would mark the passage of time. No signs of the teeming life that once covered its surface would be visible. The frozen atmosphere would create its own strange landscape. Nitrogen snow, deposited first because nitrogen freezes at a higher temperature than oxygen, would form the bottom layers. Oxygen snow would accumulate on top, creating a distinct stratification. In some places, the frozen gases might pile into drifts and dunes, sculpted by the slight differences in deposition rates across the landscape. In others, the layer might be thin, exposing the ice beneath, the frozen remnants of what had once been oceans, lakes, and rivers. Beneath the frozen air, the ice sheet covering the former oceans would continue to thicken slowly, century by century. The oceans would not freeze solid, not for billions of years, if ever, but the ice layer would eventually reach depths of many kilometers in some regions. The pressure of all that ice would compress the deeper layers, changing the crystal structure of the frozen water, creating forms of ice that don't exist on present-day Earth's surface. The continents, now merely topographical features beneath a uniform blanket of frozen gases, would be unrecognizable. Cities would be buried. Mountains would be smoothed. The entire surface would take on a homogeneous appearance. The diversity of Earth's geography erased by the indiscriminate deposition of atmospheric snow. And the silence. There would be no sound on this frozen Earth. No wind, no waves, no animal calls, no human voices. Sound requires a medium to travel through, and with the atmosphere frozen solid, that medium would no longer exist at the surface. If any observer stood on that frozen plain, they would experience absolute silence, the complete absence of any acoustic vibration. Even the loudest scream would produce no sound, its energy absorbed immediately by the frozen gases surrounding the screamer. This would be the final state of Earth's surface. Frozen, silent, dark, and dead. A monument to what had been, preserved in ice and frozen air for as long as the universe endured. In the face of cosmic catastrophe, humanity would not go gently into that frozen night. Even as the surface of Earth transformed into an airless wasteland of ice and frozen atmosphere, even as billions died in the initial weeks and months of darkness, pockets of human survivors would be fighting desperately to extend our species' existence for as long as possible. The methods would be extreme. The conditions would be brutal. The outcome would be uncertain. But the human will to survive is among the most powerful forces on this planet. and it would be on full display in the final chapter of surface-dwelling humanity. Let us consider where and how people might survive, and for how long. The key to survival in a sunless world is simple to state, but difficult to achieve. You need heat that doesn't come from the sun. Fortunately, the sun is not Earth's only source of warmth. Our planet generates its own heat deep in its interior and has been doing so for 4.6 billion years. This geothermal energy could be the salvation of a small fraction of humanity. The Earth's interior is hot for two reasons. Approximately 20% of Earth's internal heat is primordial, residual energy left over from the planet's violent formation. When Earth coalesced from the cloud of gas and dust surrounding the young sun, gravitational compression generated enormous amounts of heat. The core of our planet has been slowly cooling ever since, radiating that primordial heat upward through the mantle and crust. The remaining 80% of Earth's internal heat comes from radioactive decay. Deep in Earth's interior, radioactive isotopes of uranium, thorium, and potassium are continuously breaking down, releasing energy in the process. This radioactive decay generates approximately 20 to 30 trillion watts of power, a prodigious amount, though spread across the entire volume of the Earth. At the surface, most of this geothermal energy is completely overwhelmed by solar radiation. The sun delivers about 1.4 kilowatts of energy per square meter to Earth's surface at noon on a clear day. Geothermal heat flow, by contrast, averages only about 80 milliwatts per square meter, roughly 17,000 times less. Under normal circumstances, geothermal energy is a negligible factor in surface temperatures. But in a world without the sun, geothermal energy suddenly becomes precious beyond measure. There are places on Earth where geothermal heat flow is concentrated, where hot rock lies close to the surface, where volcanic activity heats groundwater, where the planet's interior fire burns close enough to touch. These geothermal hotspots would become the last refuges of surface-dwelling humanity. Yellowstone National Park in the western United States sits atop one of the largest volcanic systems on Earth. Beneath the park lies a massive magma chamber that has erupted catastrophically in the past and will likely do so again in the distant future. But between eruptions, this magma chamber provides an enormous reservoir of geothermal heat. Hot springs, geysers, and fumaroles dot the landscape, testament to the molten rock lurking just a few kilometers below. Iceland, that remarkable island straddling the mid-Atlantic ridge, is another geothermal paradise. Sitting atop a continental rift where two tectonic plates are pulling apart, Iceland has access to essentially unlimited geothermal energy. More than 25% of the country's electricity already comes from geothermal power plants, and the entire capital city of Reykjavik is heated by hot water piped directly from the ground. In a sunless world, Iceland's geothermal resources could keep a substantial population warm and powered for centuries. Other geothermal hotspots around the world, the volcanic regions of New Zealand, the geysers of Chile and Japan, the hot springs of East Africa's Rift Valley, could similarly serve as refuges. Communities that established themselves at these locations before the cold became too intense might be able to maintain habitable temperatures indefinitely, drawing on the Earth's own internal fire to survive. But geothermal areas are not the only option for survival. Humans have another source of concentrated energy at our disposal: nuclear power. A nuclear reactor, once fueled and started, can operate for years or decades without any input from the sun. The uranium fuel contains energy generated by ancient supernovae, stored in atomic nuclei for billions of years, waiting to be released through controlled fission. In the months following the sun's disappearance, any nation with nuclear capabilities would likely begin crash programs to build enclosed survival habitats around existing nuclear plants. These facilities could provide electricity for heating, lighting, and the operation of essential systems. With enough planning and resources, substantial communities could be maintained around these artificial heat sources for as long as the reactors lasted. Underground bunkers, always a fixture of apocalyptic planning, would take on new urgency. Deep underground, the temperature is remarkably stable, typically around 10 to 15 degrees Celsius, regardless of surface conditions. This is because the rock insulates the underground space from surface temperature fluctuations while conducting a small amount of geothermal heat upward from below. At depths of a few hundred meters, humans could escape the worst of the surface cold without any active heating at all. The challenge would be maintaining a breathable atmosphere, growing food, and managing all the other necessities of life in an enclosed underground environment. But these are engineering problems, not fundamental physical barriers. With sufficient preparation and resources, underground survival colonies could potentially maintain human life for thousands of years. The real question is, how many people could survive, and for how long? In the worst-case scenario, the sun disappears suddenly with no warning. The answer is probably very few. There simply wouldn't be time to construct adequate shelters, stockpile supplies, and establish self-sustaining systems. Billions would die in the first weeks and months, frozen on the surface, or killed in the chaos of societal collapse. Perhaps millions might manage to reach geothermal areas or underground refuges, but most of those would die as food supplies ran out or systems failed. But remember, this is a thought experiment. The sun isn't actually going to disappear suddenly, and if we're allowing ourselves to imagine impossible scenarios, let's also imagine that humanity had some warning, thousands of years of advance notice perhaps, to prepare for a sunless future. With sufficient warning, the picture changes dramatically. Humanity could construct massive underground complexes, powered by nuclear reactors or geothermal energy, capable of housing millions of people. These complexes would need to be fully self-sustaining, capable of producing food, recycling water and air, maintaining machinery, and supporting a functional society without any external inputs. Food production would be the greatest challenge. Without sunlight, traditional agriculture is impossible, but food can be grown under artificial lights, powered by nuclear or geothermal electricity. Hydroponics and aeroponics, methods of growing plants in nutrient solutions without soil, can produce impressive yields in compact spaces. Algae cultivation could provide protein and calories efficiently. Mushrooms, which don't require light at all, could become a dietary staple. With careful resource management and advanced technology, survival colonies might support populations of millions for hundreds of thousands of years. The limits would be set by the availability of nuclear fuel, the longevity of geothermal heat sources, and the ability of enclosed societies to maintain social cohesion and technological capability across countless generations. The psychological challenges of such an existence would be profound. Humans evolved under open skies, with sunlight defining our days and seasons structuring our years. A life lived entirely underground in artificial light, with no hope of ever seeing the natural world again, would be profoundly alien to everything in our evolutionary heritage. Depression, anxiety, and other mental health challenges would likely be endemic. Entire philosophies and religions would need to evolve to help people find meaning in such a constrained existence. But humans are remarkably adaptable. Within a few generations, the underground existence might come to seem normal, the only life anyone had ever known. Children born in the survival colonies would have no memory of sunlight, no concept of seasons, no experience of open sky. To them, the cramped tunnels and artificial lights would simply be reality. These new generations might watch documentaries in disbelief about the ancient times when their ancestors walked freely on the surface of a warm, bright planet circling a star. The very concept might seem almost mythological. A golden age in the distant past, too wonderful to have ever really existed. The surface world would become legend, then fairy tale, then perhaps forgotten altogether. And yet, even in this reduced state, humanity would persist. Our species, which evolved on the African savanna and spread to every corner of the globe, would continue its existence in underground warrens, warmed by the Earth's own internal fire, powered by ancient starlight locked in uranium atoms, dreaming perhaps of a future that might never come. At some point, centuries or millennia in the future, the survivors might decide to seek a new home. Earth, hurtling through space at 30 kilometers per second, would eventually pass near other stars. The journey would take millions of years, but time would have little meaning to a species with nowhere else to go. If Earth were lucky enough to pass close to a star with habitable planets, the descendants of the survivors might attempt to colonize that new world, to step out of their underground refuges and feel warmth on their faces for the first time in thousands of generations. It's a slim hope. The distances between stars are vast, and the probability of Earth passing close enough to a suitable system is low. But it's not zero, and in a universe where the impossible has already happened, where the sun has vanished and humanity has survived, who's to say what else might be possible? Spaceflight, oddly enough, would become easier in one respect. With no atmosphere to fight through, launching spacecraft from Earth's surface would require far less energy. The frozen, airless surface of the planet might become a launching pad for expeditions to any nearby star system Earth happened to approach. The last survivors of humanity might ultimately leave Earth behind entirely, seeking a new home among the stars, carrying the memory of their lost world with them into the cosmic void. This is the strange hope that might sustain those underground survivors through the long millennia of darkness, that although their world has died, their species might yet find a future among the stars. It's a thin thread to cling to, but in the darkness, even the thinnest thread of hope can make all the difference. Consider what life would actually be like for these survivors across the generations. They would never see natural light again. Everything would be lit by artificial sources, LEDs, fluorescent tubes, perhaps bioluminescent organisms engineered for the purpose. The quality of this light would be fundamentally different from sunlight, lacking the full spectrum that human eyes evolved to perceive. Colors would seem slightly off, slightly wrong, in ways that might be difficult to articulate, but impossible to ignore. The air they breathed would be recycled endlessly, scrubbed of carbon dioxide, and replenished with oxygen by machines or carefully cultivated plants. There would be no fresh breezes, no scent of rain, no smell of growing things, except in the carefully controlled agricultural sections. The air would have a quality, neither unpleasant nor pleasant, simply artificial, that would become the new normal, but would never quite feel right to those who remembered the world above. Food would be monotonous, but sufficient. The survivors would eat primarily cultivated crops, potatoes, grains, leafy vegetables, supplemented by algae, mushrooms, and perhaps some carefully maintained fish or poultry. Meat from large mammals would become rare and precious, then disappear entirely. The varied cuisines of the surface world would become memories, then legends, then forgotten entirely. Water would be precious beyond measure. Every drop would be recycled, purified, and recycled again. The survival colonies would be closed systems, losing almost nothing to the outside world. The water in a survivor's cup might have passed through hundreds of bodies before reaching them, might have been ice in the frozen ocean above, might have fallen as rain on the surface world millennia before the catastrophe. Social structures would evolve to meet the unique pressures of underground life. Privacy would be limited. In enclosed spaces, everyone's business tends to become everyone else's business. Conflict resolution would become critically important, as there would be nowhere to escape to if relationships broke down. New forms of governance might emerge, adapted to the realities of survival in a world where every resource was limited and every person was essential to the community's continued existence. Mental health would be perhaps the greatest ongoing challenge. Depression, anxiety, claustrophobia, something like seasonal affective disorder without any seasons, all would be endemic. The survivors would need to develop new psychological tools, new rituals, new sources of meaning to maintain morale across the generations. Those who couldn't adapt psychologically would become burdens on the community or would simply give up, their passing reducing the population, but also reducing the strain on limited resources. Children born in the survival colonies would have no frame of reference for the world their parents lost. They would learn about the sun in history lessons, perhaps see images or videos preserved from the before times, but they would never truly understand what it meant to feel warmth on their faces, to see a blue sky, to watch clouds drift lazily by on a summer afternoon. The loss would be abstract to them in a way it could never be to their parents and grandparents. And yet, humans adapt. Within a few generations, the underground life would simply be life, the only life anyone knew, the only life anyone could imagine. The survival colonies would develop their own cultures, their own traditions, their own ways of finding joy and meaning in existence. Children would laugh and play in the artificial corridors. Young people would fall in love and start families. Old people would tell stories of the past and be half-believed at best, their tales of a warm, bright world seeming like obvious exaggeration. Life would go on, diminished but persistent, for as long as the energy lasted and the machines kept running. And who knows, perhaps those generations born in darkness would be happier in their way than we are. Having never known what they missed, they couldn't mourn it. The underground world would be their world, their home, and they would love it with all the fierce attachment that humans always develop for the places where they live and raise their children. That is the stubborn miracle of human existence. We find meaning, we find purpose, we find reasons to go on, even in the darkest circumstances imaginable, even in a literal darkness that never ends. While humanity struggles to survive in underground bunkers and geothermal refuges, there would be other life on Earth, carrying on as if nothing had changed. Deep beneath the frozen surface, far below the ice-locked oceans, in places the sun's light has never reached, entire ecosystems would continue to thrive, utterly indifferent to the cosmic catastrophe that had claimed the surface world. These creatures have never depended on the sun. They wouldn't notice it was gone, and they would continue their ancient cycles of life and death for billions of years into the future, long after the last human survivor had drawn their final breath. This is the story of Earth's sunless ecosystems and of the remarkable organisms that call them home. For most of human history, we assumed that all life on Earth ultimately depended on the sun. Photosynthesis captures solar energy and converts it into the chemical energy that powers nearly every ecosystem we can see. Plants use sunlight to grow. Herbivores eat plants. Carnivores eat herbivores. Decomposers break down the dead. It's a chain that stretches from the humblest blade of grass to the mightiest predator. And every link in that chain can be traced back to sunlight captured by photosynthetic organisms. This assumption seemed so obvious, so fundamental, that nobody seriously questioned it. How could life exist without the sun? Where else could the energy come from? Then, in 1977, everything changed. On February 17th of that year, a research expedition aboard the vessel Knorr arrived at the Galapagos Rift, a geological feature on the floor of the Pacific Ocean, where two tectonic plates are slowly pulling apart. The scientists were searching for hydrothermal vents, places where seawater seeps down through cracks in the ocean floor, gets superheated by contact with magma, and shoots back up as underwater geysers. Such vents had been theorized but never directly observed. What the researchers found exceeded their wildest expectations. Using Angus, a deep-sea camera system towed behind the ship, they captured images of something unprecedented. Dense communities of living organisms clustered around the hydrothermal vents, thriving in an environment of crushing pressure, total darkness, and toxic chemicals that should have been lethal to any known life form. Giant clams with blood-red flesh, bizarre pale crabs, swaying forests of tube-like structures that turned out to be enormous worms. The following expedition, in 1979, used the submersible Alvin to explore these vent communities in person. What the scientists found changed our understanding of life itself. At a site they dubbed the Rose Garden for the red-tipped tube worms that dominated it. Researchers discovered Riftia pachyptila, the giant tube worm. These extraordinary creatures can grow up to 3 meters, nearly 10 feet in length, making them among the largest invertebrates known. They have no mouth, no stomach, no digestive system of any kind. They shouldn't be able to survive, let alone thrive. Yet there they were, waving their crimson plumes in the shimmering water, packed together in dense colonies around the hydrothermal vents. How could animals with no digestive system possibly feed themselves? The answer revolutionized biology: chemosynthesis. Inside the giant tube worms, packed into a specialized organ called the trophosome, live trillions of bacteria. These bacteria are capable of something remarkable. They can produce organic molecules, sugars, proteins, the building blocks of life, using chemical energy rather than light energy. Instead of photosynthesis, they perform chemosynthesis. The process works like this. Hydrothermal vents spew out water rich in hydrogen sulfide, a toxic gas that smells like rotten eggs and is lethal to most organisms. But the bacteria living inside the tube worms can oxidize this hydrogen sulfide, breaking it down and capturing the chemical energy released in the process. They use this energy to convert carbon dioxide from the seawater into organic compounds, exactly the same end result as photosynthesis, achieved through completely different means. The tube worms provide the bacteria with a safe home and access to the chemicals they need. The bacteria provide the tube worms with all the nutrition they require. It's a perfect symbiotic relationship, and it operates entirely independently of the sun. The discovery of chemosynthesis as the basis for an entire ecosystem wasn't entirely unexpected. Bacteria capable of chemosynthesis had been known since the late 19th century. But nobody had imagined that chemosynthetic organisms could support such abundant and diverse communities. The prevailing assumption had been that without photosynthesis, life could exist only in sparse, marginal forms, a few hardy bacteria scraping out an existence in extreme environments. The Galapagos Rift vents showed that chemosynthesis could support a thriving ecosystem as rich and complex as any coral reef. Tube worms, mussels, clams, crabs, shrimp, fish, octopuses, hundreds of species have been found living at hydrothermal vents, most of them unknown to science before 1977. It was, as one of the geologists on the original expedition put it, a discovery comparable to Columbus finding the Americas. Since 1977, hydrothermal vent communities have been discovered throughout the world's oceans, wherever tectonic activity brings heat and chemicals to the seafloor. The Mid-Atlantic Ridge, the East Pacific Rise, the Indian Ocean, the Arctic Ocean. Each new vent field reveals its own unique assemblage of species, though the basic ecology is always the same. Chemosynthetic bacteria at the base of the food web, supporting a diverse community of larger organisms. Other types of chemosynthetic ecosystems have also been discovered. Cold seeps, places where methane and other hydrocarbons leak from the seafloor, support communities similar to hydrothermal vents, powered by methane-eating bacteria rather than sulfide-eating ones. Deep in the ocean sediments, far from any vent or seep, bacteria have been found living on chemical energy alone, processing the sparse nutrients that filter down from above. The implications for a sunless Earth are profound. These chemosynthetic ecosystems would not notice if the sun disappeared. They exist in total darkness already. They derive no energy from sunlight. Their food web is entirely independent of photosynthesis. As long as Earth's internal heat continues to drive hydrothermal circulation, and it will for billions of years, these ecosystems will continue to function. In fact, the deep ocean might actually benefit from the sun's disappearance in one perverse way. Currently, most of the organic matter that reaches the deep sea floor comes from above, the remains of photosynthetic organisms and the animals that eat them, sinking slowly through kilometers of water column. This marine snow provides food for many deep-sea organisms that don't live near hydrothermal vents. Without photosynthesis, this rain of organic matter would cease. But the vent communities don't depend on it anyway. They might actually face less competition for the chemical resources they need, as other deep-sea organisms die off from starvation. The oceans would freeze over on their surfaces, yes, but ice floats, and ice insulates. Below the growing ice layer, liquid water would persist, kept liquid by pressure, by salt content, and by the geothermal heat flowing up from the ocean floor. The hydrothermal vents would continue pumping out superheated water, creating oases of warmth in the frigid deep. The chemosynthetic bacteria would continue converting chemical energy into biological energy. The tube worms would continue waving their crimson plumes. The crabs would continue scuttling across the basalt. Life would go on. For how long? The answer is almost incomprehensible. Billions of years. Earth's internal heat is not infinite, but it is vast. The radioactive elements that provide 80% of that heat have half-lives measured in billions of years. Uranium-238 has a half-life of 4.5 billion years, uranium-235, 700 million years, thorium-232, 14 billion years, potassium-40, 1.25 billion years. These elements will continue producing heat for eons to come, slowly declining but never stopping entirely. Even after tens of billions of years, Earth's interior would retain significant heat, enough to drive hydrothermal circulation, enough to support chemosynthetic ecosystems. The vent communities that exist today might have descendants living at the same vents or their successors for longer than the current age of the universe. This is perhaps the most remarkable outcome of the sun's hypothetical disappearance. Earth would not become a dead world. it would continue to harbor life, reduced, certainly, from the teeming diversity of the surface biosphere, but life nonetheless. Simple, hardy life, thriving in the darkness, utterly unaware that anything had changed above. And here's a thought that should keep you awake at night. What if this has happened before? Not on Earth necessarily, but somewhere else in the universe. Our galaxy contains hundreds of billions of stars, and most of those stars probably have planets. Some of those planets may have formed with internal heat and geological activity. Some may have oceans, some may have hydrothermal vents. What if there are worlds out there that never had a sun? Rogue planets wandering the darkness between stars, kept warm only by their internal heat, harboring deep ocean ecosystems that have never known light. What if chemosynthesis, not photosynthesis, is the more common form of life in the universe? Life that doesn't need stars, that thrives in the endless dark, that might be far more widespread than our sun-dependent biosphere? The moons of the outer solar system offer tantalizing hints. Europa, orbiting Jupiter, is covered in ice but almost certainly has a liquid ocean beneath that frozen shell, warmed by tidal heating from Jupiter's massive gravity. Enceladus, a tiny moon of Saturn, shoots geysers of water into space from hydrothermal vents on its ocean floor. These worlds receive only feeble light from the distant sun, but they have heat and water and chemistry, the same ingredients that support life at Earth's deep-sea vents. If the sun disappeared tomorrow, the vent communities at the bottom of Earth's oceans would carry on. They would continue their ancient cycles of life for billions of years, their descendants perhaps evolving into new forms as the eons passed. And if Earth were eventually captured by another star, if the frozen surface thawed and the oceans melted and sunlight once again reached the planet's surface, those deep-sea survivors might be the ancestors of whatever life emerged to colonize the renewed surface world. The sun giveth, and the sun taketh away. But some life has never needed the sun's blessing at all. In the darkness of the deep, life finds a way. The implications of this extend far beyond our own planet. If life can thrive without sunlight on Earth, powered entirely by chemical energy from the planet's interior, then the same could be true on countless other worlds throughout the universe. We have traditionally focused our search for life on planets within the habitable zone of their parent stars, the narrow band of orbital distances where temperatures allow liquid water to exist on the surface. But the discovery of hydrothermal vent ecosystems suggests that this focus may be far too narrow. Consider the moons of our outer solar system. Europa, the fourth largest moon of Jupiter, is covered in a shell of ice roughly 15 to 25 kilometers thick. But beneath that ice, warmed by tidal heating from Jupiter's immense gravitational pull, lies a global ocean containing twice as much water as all of Earth's oceans combined. That ocean is in contact with a rocky seafloor, exactly the conditions needed for hydrothermal vent formation. If Europa has hydrothermal vents, it could have chemosynthetic life. The same chemical reactions that power Earth's vent communities could be occurring right now on a moon of Jupiter, just as they have been occurring on Earth for billions of years. NASA and the European Space Agency are planning missions to Europa specifically to investigate this possibility. Enceladus, a tiny moon of Saturn only 500 kilometers across, puts on an even more dramatic show. Geysers of water vapor and ice particles shoot hundreds of kilometers into space from cracks near the moon's south pole. Analysis of this material by the Cassini spacecraft revealed organic molecules, salts, and silica particles consistent with hydrothermal activity on the ocean floor. Enceladus is actively venting water from an internal ocean into space. and that water shows signs of hydrothermal processing. These discoveries have revolutionized the field of astrobiology. The universe might be far more populated than we imagined, not with civilizations building radio telescopes, but with simple chemosynthetic organisms thriving in the depths of ocean worlds we never thought to examine. Life might be everywhere in the cosmos, not basking under the light of stars, but hidden in the dark beneath ice shells, powered by the internal heat of planets and moons. The vent communities at the bottom of Earth's oceans represent a profound lesson in the resilience and adaptability of life. They prove that the sun, that seemingly essential source of all energy and warmth, is not actually necessary for life to exist. Life can find other energy sources. Life can thrive in conditions that seem utterly hostile to our surface-dwelling sensibilities. Life, given any opportunity at all, tends to persist. If the sun disappeared tomorrow, the vent communities would carry on. Their descendants might still be there billions of years from now, when Earth approaches another star, when the ice melts, when sunlight once again reaches the planet's surface. Those deep-sea survivors might be the ancestors of whatever life emerged to colonize the renewed surface world, just as, billions of years ago, chemosynthetic organisms in Earth's primordial oceans might have been the ancestors of everything that has ever lived on our planet's surface. The sun giveth, and the sun taketh away. But some life has never needed the sun's blessing at all. In the eternal darkness of the deep ocean, in the superheated water gushing from volcanic vents, in the chemical soup of hydrogen sulfide and methane, life has found a way to persist. And it would continue to persist, sun or no sun, for as long as the Earth's internal fires continued to burn. That is perhaps the most hopeful message we can take from this thought experiment. Earth would not become a dead world if the sun disappeared. It would continue to harbor life, reduced, certainly, from the teeming diversity of the surface biosphere, but life nonetheless. Simple, hardy life, thriving in the darkness, utterly unaware that anything had changed above. Life that doesn't need the sun at all. The night sky seems peaceful and orderly. Look up on a clear evening, and you'll see thousands of stars scattered across the heavens, arranged in familiar constellations that have guided human navigation and inspired human mythology for millennia. Orion the Hunter, the Big Dipper, the Southern Cross. These patterns appear fixed and eternal, unchanging monuments in a changing world. But this appearance of stillness is an illusion. Every single star you can see is moving, not just orbiting the center of our galaxy, though they're doing that too. The sun completes one orbit around the Milky Way's core every 225 to 250 million years, carrying the entire solar system along for the ride. The stars are also moving relative to each other, drifting through the galaxy at speeds of hundreds of thousands of kilometers per hour, changing cosmic neighborhoods constantly. The constellations we see tonight are not the constellations our distant ancestors saw, and they are not the constellations our distant descendants will see. Over thousands of years, the familiar patterns slowly distort as individual stars move at different speeds and in different directions. Over millions of years, the constellations become unrecognizable. Over billions of years, the entire stellar neighborhood transforms completely. Fortunately, space is inconceivably vast. The distances between stars are so enormous that collisions are almost impossibly rare. Even in the relatively crowded central regions of our galaxy, where stars are packed thousands of times more densely than in our neighborhood, direct stellar collisions are events of cosmic rarity. But here's the crucial point. Stars don't have to collide with anything to cause serious problems. They don't have to touch our solar system to disrupt it catastrophically. They just have to come close enough for their gravity to be felt. Gravity, as we've discussed, attracts every piece of matter to every other piece of matter in the universe. You are being gravitationally attracted right now to every star in the Milky Way, to every galaxy in the observable universe, to every atom in the cosmos. The forces are infinitesimal, far too weak to measure, let alone feel. But they exist. As distance decreases, gravitational force increases dramatically. A star that passes within a light year of our sun exerts a far stronger gravitational pull than a star 100 light years away, and the solar system contains countless objects that are only loosely bound to the sun, objects that could be torn away by even a modest gravitational perturbation. The most vulnerable region is the Oort cloud. This hypothetical structure, never directly observed but strongly implied by the orbital characteristics of long-period comets, is believed to be a vast spherical shell of icy bodies surrounding the solar system at distances of roughly 2,000 to 200,000 astronomical units from the Sun. That's between 0.03 and 3.2 light years, depending on which boundary you're measuring, putting the outer edge of the Oort cloud nearly a quarter of the way to the nearest star. The Oort cloud is believed to contain trillions of cometary bodies, ranging from small chunks of ice a few meters across to objects potentially as large as small planets. These bodies formed in the inner solar system billions of years ago, then were gravitationally ejected to the outer reaches by encounters with the giant planets. There they remain, in cold storage, their orbits so distant that the sun's gravitational grip on them is tenuous at best. A passing star, even one that never comes close to the inner solar system, can wreak havoc on the Oort cloud. Its gravity tugs on the loosely bound cometary bodies, changing their orbits, sometimes sending them plunging toward the inner solar system on trajectories that take millions of years to complete. This isn't theoretical. It has already happened, and we have evidence of it. About 70,000 years ago, around the time when anatomically modern humans were beginning their migration out of Africa, a small binary star system passed through the outer reaches of our solar system. The primary component is a red dwarf star with approximately 86 Jupiter masses, barely massive enough to sustain hydrogen fusion in its core. The secondary is a brown dwarf, a failed star with about 65 Jupiter masses, too small to ignite fusion at all. This system, discovered in 2013 by astronomer Ralph Dieter Schultz, and now known as Schultz's star, approached to within approximately 52,000 astronomical units of the Sun, about 0.82 light years, or roughly 7.8 trillion kilometers. That's close by astronomical standards, about 5 times closer than the nearest star today, Proxima Centauri, at 4.2 light years. At that distance, Schultz's star passed through the outer Oort cloud with 98% probability according to orbital simulations. Its gravity would have pulled on the cometary bodies in that region, altering their orbits and potentially sending some of them toward the inner solar system. If any of those perturbed comets are heading our way, they haven't arrived yet. The journey from the Oort cloud to the inner solar system takes roughly 2 million years at typical cometary velocities. Objects disturbed by Schultz's star 70,000 years ago could still be falling toward us, their rendezvous with the inner planets potentially millions of years in the future. Recent research has found evidence of this ancient flyby. In 2018, astronomers analyzing the orbits of nearly 340 objects with hyperbolic trajectories, orbits that will eventually take them out of the solar system entirely, found a statistically significant clustering. Instead of being evenly distributed across the sky, many of these objects appeared to be coming from the same direction, the constellation Gemini, which aligns with the trajectory of Schultz's star's close approach. The implication is remarkable. We can see the gravitational signature of a stellar encounter that happened 70,000 years ago, written in the orbital dynamics of distant objects. Our prehistoric ancestors might have seen Schultz's star as a dim red point in the night sky, too faint for the naked eye under normal circumstances, but possibly visible during stellar flares. They had no way of knowing that this unremarkable visitor was rearranging the furniture in our cosmic neighborhood. Schultz's star was probably not the first stellar intruder, and it certainly won't be the last. Stars are expected to pass through the Oort cloud approximately once every 100,000 years on average. An approach as close as Schultz's star, within about 52,000 AU, is estimated to occur roughly once every 9 million years. These are averages, of course. The actual timing is random, governed by the chaotic dance of stellar motions in our galactic neighborhood. The danger from such encounters is not that a passing star will directly affect Earth or the inner planets. At the distances involved, the gravitational perturbation to planetary orbits would be negligible. The danger is indirect. A passing star can dislodge comets from the Oort cloud and send them cascading into the inner solar system over the following millions of years. A significant comet bombardment could have catastrophic consequences for life on Earth. We know that large impacts have caused mass extinctions in the past, the most famous being the Chicxulub impact 66 million years ago that ended the age of dinosaurs. If a stellar flyby were to trigger a sustained increase in the rate of large impacts, the consequences could be devastating. But here's an encouraging thought. We would see it coming. Stars don't sneak up on solar systems. Their approaches unfold over thousands or millions of years, giving us ample time to observe, calculate, and prepare. With modern astronomy and the continuous monitoring of stellar positions and velocities by missions like the European Space Agency's Gaia spacecraft, we can predict stellar flybys centuries or millennia in advance. The Oort cloud might seem impossibly distant and invisible, but we can calculate which stars will pass through it and when. We can estimate the probability of comet showers and plan accordingly. We cannot stop a star from passing close to our solar system, but we could potentially prepare for and mitigate the consequences. The early solar system was far more chaotic than the orderly arrangement we see today. In the first few 100 million years after the sun's formation, the planets were still migrating, jostling for position, occasionally ejecting smaller bodies into the outer reaches of the system or beyond. The Oort cloud itself is probably composed of objects that were ejected from the inner solar system during this tumultuous era. During this period, the young sun was still part of its birth cluster, a loose association of stars that formed from the same molecular cloud. These sibling stars would have been much closer to each other than the typical stellar separations we see today, and encounters would have been far more frequent and intense. Some astronomers have speculated that the sun might have captured some of its Oort cloud objects from other stars in its birth cluster, and might have lost some of its original members to those same stars. The Oort cloud we have today might be a mixed population, containing both native-born comets and immigrants from other stellar systems. The birth cluster has long since dispersed, its members scattered across the galaxy by billions of years of differential motion. But occasionally, old siblings pass by, stars that share the sun's origin but have long since gone their separate ways. Schultz's star might or might not be one of these. Its exact birthplace is difficult to determine. What we know for certain is that the apparently peaceful night sky is actually a dynamic environment with stars constantly in motion, occasionally passing close enough to perturb the delicate gravitational balance of our solar system. We have weathered such encounters before, and we will weather them again. But there is one approaching visitor that deserves special attention, a star that will come far closer than Schultz's star ever did, and whose passage through our neighborhood could have far more dramatic consequences. That star is called Gliese 710, and it is already on its way. Its story and the threat it poses will occupy our attention in the next section. For now, let us simply note that the cosmos is not as peaceful as it appears. The ordered dance of the planets, the seemingly fixed patterns of the stars, the comforting regularity of day and night and seasons, all of these exist within a larger context of cosmic motion and gravitational interaction that occasionally disrupts the pleasant equilibrium we have come to expect. The night sky only seems peaceful because we live for such a short time. On longer timescales, thousands, millions, billions of years, the stars are in constant, tumultuous motion, careening through the galaxy, occasionally coming close enough to remind us that our solar system is not an island, but a ship sailing through a vast and sometimes dangerous sea. And sometimes, the sea sends visitors, but the story of stellar encounters is not all doom and gloom. These cosmic interactions have shaped our solar system in ways that might have been essential for life to develop here at all. The early solar system, in the first few 100 million years after the sun's formation, was a fundamentally different place than the orderly arrangement we see today. Planets were migrating, trading places, sometimes ejecting each other entirely. The giant planets, Jupiter and Saturn in particular, likely formed closer to the sun than they are now, then migrated outward through gravitational interactions with the disk of gas and debris that surrounded the young star. This migration scattered countless smaller bodies throughout the solar system. Some were flung into the inner solar system, bombarding the young Earth with water-rich asteroids and comets that may have delivered the oceans we now depend on. Others were ejected to the outer reaches, populating the Kuiper Belt and Oort cloud with the icy remnants of the solar system's chaotic youth. And some of those bodies may not have originated in our solar system at all. The sun formed in a stellar nursery, surrounded by dozens or hundreds of sibling stars born from the same molecular cloud. In those early days, the young stars were much closer together than the typical stellar separations we see today. Gravitational interactions between these siblings could have exchanged material, objects that formed around one star captured by another, becoming permanent members of their new solar system. Some of the comets in our Oort cloud might be immigrants from other stellar systems, captured billions of years ago when our cosmic neighborhood was more crowded. If so, they would carry information about conditions around those other stars, preserved in ice for billions of years, waiting to be examined if we could only reach them. The discovery of interstellar objects like Oumuamua in 2017 and Comet Borisov in 2019 proves that such exchanges do occur. These visitors, clearly originating from other stellar systems based on their hyperbolic trajectories, passed through our solar system and continued on their way. But others might have been captured, becoming permanent residents. The boundary between our material and foreign material might be far blurrier than we once assumed. This cosmic mixing has implications for the distribution of life in the universe. If life can survive the cold journey through interstellar space, frozen in ice, dormant but not dead, then stellar encounters could spread life from one system to another. A comet dislodged from one star's Oort cloud might eventually fall into another star's inner system, delivering whatever microorganisms it carried to a new world. This hypothesis, called panspermia, remains speculative but not impossible. We know that bacterial spores can survive extreme conditions, vacuum, radiation, cold, for extended periods. We know that rocks can be blasted off one planet and land on another. Martian meteorites have been found on Earth, having made the journey through space over millions of years. If microorganisms can survive such journeys, then stellar encounters might serve not only to threaten life, but also to spread it across the galaxy. The night sky, in this view, becomes not just a collection of distant lights, but a network of interconnected worlds, occasionally exchanging material through the slow dance of gravitational encounters over billions of years. Life on Earth might have arrived from elsewhere. Life on Earth might have been sent elsewhere, carried by ejected comets to destinations we will never know. This is the cosmic context in which our solar system exists, not as an isolated island, but as a node in a vast galactic network, influenced by and influencing countless other stellar systems across millions and billions of years. The stellar encounters that seem so threatening, the close passes that disrupt our Oort cloud and send comets raining toward the inner planets, are also the encounters that connect us to the wider universe, that remind us we are part of something much larger than our own small corner of space. Schultz's star passed through our solar system 70,000 years ago. Other stars have done so before, and others will do so in the future. We are not alone in the cosmic void. We are participants in a grand, slow dance of gravitational interaction that has been choreographed across billions of years and will continue for billions more. And on that note of cosmic connection, let us turn our attention to the visitor that concerns astronomers most, the star that is already on its way, the star that will pass closer than any known encounter in the past or foreseeable future. Gliese 710 is coming, and its story, the threat it poses, and the preparations we might make will occupy our attention in the sections to come. There is a star heading toward us right now. It's invisible to the naked eye, a dim orange point in the constellation Serpens Cauda, the serpent's tail, unremarkable among the billions of stars in our galaxy. You could point a backyard telescope at it and see nothing special, just another faint stellar ember, magnitude 9.69, too dim by far for human eyes to detect without optical assistance. Its name is Gliese 710, and in approximately 1.29 million years, it will become the brightest star in our night sky. This isn't a prediction based on speculation or theoretical models. This is established observational fact, refined and confirmed by some of the most precise measurements in the history of astronomy. The European Space Agency's Gaia spacecraft, a $billion mission specifically designed to map the positions and motions of over 1 billion stars, has tracked Gliese 710's trajectory with unprecedented accuracy. We know where it's going. We know when it will arrive. And we know that its arrival will mark the closest stellar encounter our solar system has experienced in recorded history, and quite possibly the closest it will experience for millions of years to come. Let us meet our future visitor. Gliese 710 is what astronomers call a K-type main sequence star, sometimes described as an orange dwarf. It sits on the cooler, dimmer end of the stellar spectrum, larger and hotter than a red dwarf like Proxima Centauri, but smaller and cooler than our yellow sun. With approximately 60% of the sun's mass and a corresponding reduction in luminosity, it's the kind of star that would be utterly unremarkable if not for its trajectory through the galaxy. Currently, Gliese 710 lies approximately 62.3 light-years from Earth, a vast distance by human standards, but practically next door by cosmic ones. For comparison, the nearest star to our Sun, Proxima Centauri, orbits at about 4.2 light-years distant. Gliese 710 is currently about 15 times farther away than our nearest stellar neighbor, but it's getting closer, much closer. Gliese 710 is moving toward the solar system at a velocity of approximately 1,500 kilometers per hour relative to us, fast by terrestrial standards, though not unusually so for stellar motions. This works out to roughly 14.5 kilometers per second, a respectable clip that has earned Gliese 710 classification as a rogue star, though not quite fast enough to be considered a true runaway. It's simply a star on a trajectory that happens to intersect with our neighborhood, and what a trajectory it is. Based on the most recent data from Gaia's third data release, astronomers have calculated that Gliese 710 will pass within approximately 10,635 astronomical units of the Sun, give or take about 500 AU due to measurement uncertainties. To put this in perspective, Pluto, at its most distant, orbits about 49 AU from the Sun. The Kuiper belt extends to perhaps 50 AU. Even the hypothetical inner edge of the Oort cloud begins around 2000 AU from the Sun. Gliese 710 will sail right through the middle of our Oort cloud, penetrating deep into the inner regions where cometary density is highest. At 10,635 AU, it will approach to within about 0.166 light-years of the Sun, roughly 1/4 of the current distance to Proxima Centauri, and about 5 times closer than Schultz's star came during its passage 70,000 years ago. This will be, without exaggeration, the closest known stellar encounter in the past or foreseeable future of our solar system. The approach will unfold over hundreds of thousands of years, far too slowly for any individual human lifetime to notice. But for astronomers watching with sufficiently precise instruments, the changes would be dramatic. At its current distance, Gliese 710 displays almost no proper motion. Its movement across the sky is negligible because it's heading almost directly toward us. But as it approaches, this will change. At closest approach, Gliese 710's proper motion will peak at approximately 1 arcminute per year, a rate of apparent movement that would be noticeable over a single human lifespan. Observers could watch this intruder star creep across the constellations, year by year, a visible reminder that the cosmos is not as static as it appears, and the star itself would be spectacular. At its closest approach, Gliese 710 would shine with an apparent magnitude of approximately -2.7, roughly equivalent to the planet Jupiter at its brightest, and considerably brighter than any fixed star in our current night sky. It would be visible in broad daylight, a distinct orange point of light hanging in the heavens, too bright to be ignored. Its angular diameter would reach about 0.1 arcseconds, larger than any star visible from Earth today, more than twice the angular diameter of Betelgeuse, the famous red supergiant in Orion. With a modest telescope, observers might actually be able to resolve Gliese 710 as a tiny disk rather than a point of light, something impossible with any other star at present. For observers alive at that time, if any observers exist, Gliese 710 would be an unmissable presence in the sky, a glowing orange beacon marking the closest star humanity has ever known. But the beauty of this celestial display would come with a price. As Gliese 710 plows through the Oort cloud, its gravity would tug on the trillions of icy bodies orbiting there in cold storage. Most of these objects are only loosely bound to the Sun, their orbits so distant and their velocities so slow that even modest gravitational perturbations can significantly alter their trajectories. A passing star, even at 10,000 AU, exerts considerable gravitational influence on such loosely held objects. The result would be a cosmic game of gravitational billiards played out over millions of years. Some Oort cloud objects would be accelerated and ejected from the solar system entirely, flung into interstellar space to become rogue comets wandering the galaxy. Others would have their orbits shifted outward, moving them to even more distant regions of the cloud. But most concerning from Earth's perspective, some would be nudged inward, their orbits perturbed just enough to send them falling toward the inner solar system on trajectories that could take millions of years to complete. Studies have estimated that Gliese 710's passage could send approximately 2.4 million new comets into Earth-crossing orbits over a period of about 2 million years following the encounter. This represents roughly a 50% increase in the flux of long-period comets passing through the inner solar system, a significant uptick in the cosmic bombardment rate. Not all of these comets would hit Earth, of course. Most would pass harmlessly by, putting on spectacular shows in the night sky before swinging back out toward the Oort cloud or being ejected from the solar system entirely. But some percentage would come close enough to matter. And over millions of years, even a small percentage of millions of comets adds up to a meaningful risk. Researchers have calculated that following the Gliese 710 flyby, naked-eye comets could become a common sight in Earth's skies, perhaps as many as 10 per year visible without optical aid, compared to the 1 or 2 bright comets per decade we currently experience. The night sky would be transformed, filled with the ghostly trails of icy visitors stirred from their billion-year slumber by a passing star. The larger question, whether this comet shower would trigger mass extinctions on Earth, is harder to answer with certainty. We know that large impacts have caused mass extinctions in the past. The Chicxulub impact 66 million years ago ended the reign of the dinosaurs, and there's evidence of other major impacts correlating with extinction events throughout Earth's history. If Gliese 710's passage significantly increases the rate of large impacts, the consequences for any life on Earth could be severe. However, several factors provide some reassurance. First, the absolute probability of any individual comet striking Earth is still extremely low. Even with millions of new comets entering the inner solar system, the vast majority will miss our tiny planet by enormous margins. Space is big, and Earth is a very small target. Second, the increase in impact risk would be spread over millions of years, not concentrated in a single catastrophic event. Life on Earth has proven remarkably resilient over billions of years, surviving ice ages, supervolcanic eruptions, and previous extinction events. A gradual increase in impact rate, while concerning, might be something a healthy biosphere could adapt to over evolutionary timescales. Third, if humanity or our descendants are still around in 1.29 million years, a big if, but one we must consider, our technological capabilities would likely be sufficient to detect and deflect incoming comets long before they posed a threat. A civilization capable of surviving for over 1 million years would presumably have mastered the basic challenge of tracking and redirecting incoming space rocks. But there's a deeper lesson in the approach of Gliese 710, beyond the immediate question of comet showers and impact risks. This star's inevitable arrival demonstrates that the solar system is not an isolated island, immune to outside influence. We are embedded in a dynamic galaxy where stars are constantly moving, occasionally approaching each other, exchanging gravitational influences across the vast gulfs of interstellar space. The apparent stability of our cosmic neighborhood is, in the long run, an illusion. Stars have passed close to the solar system before. Schultz's star, 70,000 years ago, is merely the most recent confirmed example. Stars will pass close again after Gliese 710 departs, On timescales of millions and billions of years, the stellar neighborhood around the Sun is constantly changing, with new neighbors approaching and old ones receding. The Oort cloud has been stirred by countless stellar passages over the 4.6 billion years of the solar system's existence, and it will be stirred countless more times before the Sun finally dies. Gliese 710 is simply the next chapter in an ongoing story of cosmic encounters, a story that began before Earth existed and will continue long after our species has either evolved beyond recognition, spread to other stars, or vanished entirely. In 129 million years, our descendants, whoever or whatever they might be, will have front row seats to the closest stellar approach in human recorded history. Whether they view it as a threat to be managed, a scientific opportunity to be exploited, or simply a celestial spectacle to be admired, Gliese 710 will arrive on schedule, indifferent to human concerns or expectations. The coming storm approaches. We have more than 1 million years to prepare. What we do with that time will determine whether Gliese 710's passage is a footnote in human history or the beginning of its end. But there's another dimension to Gliese 710's approach that deserves consideration. The star itself likely has its own Oort cloud. Think about it. Gliese 710 is a main sequence star that has been burning hydrogen for billions of years. It almost certainly formed with a protoplanetary disk, and it may well have planets orbiting it that we haven't yet detected. And if it has planets, it quite likely has its own population of loosely bound icy bodies in the outer reaches of its gravitational influence, its own Oort cloud, filled with its own comets. When Gliese 710 passes through our solar system, the gravitational interaction will be mutual. Just as its gravity will perturb objects in our Oort cloud, our Sun's gravity will perturb objects in its Oort cloud. The two clouds will, in a sense, interpenetrate, and the resulting chaos will affect both stellar systems. Objects from Gliese 710's Oort cloud might be captured by our Sun, becoming permanent residents of our solar system. Conversely, objects from our Oort cloud might be captured by Gliese 710, departing with the intruder star as it continues its journey through the galaxy. For a brief cosmic moment, a few 100,000 years, the two stellar systems will mingle their outermost contents, exchanging material like neighboring gardens whose fences have blown down in a storm. Some of those exchanged objects might eventually find their way to the inner regions of whichever solar system captures them. Comets from around another star might one day streak through Earth's sky, bringing with them ancient ice formed in conditions utterly unlike those in our own solar neighborhood. If there are organic molecules in that ice, the building blocks of life perhaps, they would be delivered to our planet from an alien stellar system. This is not mere speculation. We know from the discovery of interstellar objects like Oumuamua and Comet Borisov that material does travel between stellar systems. The passage of Gliese 710 would simply accelerate and concentrate a process that occurs naturally, if rarely, throughout the galaxy. The scientific opportunities presented by Gliese 710's approach are as significant as the potential hazards. If humanity survives to witness it, the close passage of another star would allow observations impossible at any other time. We could study Gliese 710 in unprecedented detail, mapping its surface features, analyzing its atmosphere, perhaps even detecting any planets orbiting it. We could watch the gravitational interaction between two stellar systems play out in real time, testing our models of celestial mechanics against direct observation. We could sample material from another star's Oort cloud, comparing its composition to our own cometary bodies, learning about conditions in a different stellar nursery billions of years ago. We could track the perturbed comets as they began their long fall toward the inner solar system, cataloging them, studying them, perhaps even intercepting some for detailed examination. In short, Gliese 710's passage would be one of the greatest scientific opportunities in human history, if we're still around to take advantage of it. The question of whether humanity will exist in 1.29 million years is, of course, unanswerable. That's roughly 650 times longer than recorded human history, roughly 65,000 times longer than the span from the pyramids to now. In that time, our species could evolve into something unrecognizable, spread to other star systems, and lose all contact with our home world, develop technologies that would seem magical to us today, or go extinct through war, environmental collapse, or cosmic accident. But if we do survive, if some form of human or post-human intelligence is still present in the solar system when Gliese 710 arrives, they will face both a challenge and an opportunity unlike anything we can currently imagine. The decisions they make about how to prepare for and respond to the stellar passage will shape the future of life on Earth for millions of years to come. We cannot make those decisions for them. We cannot know what technologies they will have, what resources they will command, what values they will hold, but we can give them the best possible foundation by continuing to study stellar dynamics, to understand cometary orbits, to develop technologies for tracking and deflecting cosmic threats. Every piece of knowledge we accumulate about the solar system and its place in the galaxy is a gift to our descendants, a tool they can use when facing challenges we cannot foresee. The study of Gliese 710's approach, even now, is part of that gift. The coming storm approaches. We have more than 1 million years to prepare. And humanity's first step toward that preparation is simply to pay attention, to track the approaching star, to understand its trajectory, to model its effects, and to pass that knowledge forward to whoever comes after us. The stars are not our enemies. They are simply our neighbors, moving through the galaxy on their own trajectories, occasionally passing close enough to remind us that the cosmos is dynamic, ever-changing, and full of both danger and wonder. Gliese 710 is coming. We cannot stop it, but we can understand it, prepare for it, and perhaps even welcome it as a reminder of our place in the vast, ancient, endlessly fascinating universe we call home. Gliese 710, for all the drama of its approach, will pass safely through the outer reaches of our solar system, perturbing comets, but leaving the planets themselves undisturbed. At 10,635 AU, it will be far too distant to have any meaningful gravitational effect on Earth, Mars, Jupiter, or any of the worlds orbiting within the Sun's gravitational embrace. But what if a stellar encounter were not so gentle? What if, instead of passing through the outer Oort cloud, a star passed through the inner solar system itself, threading the needle between the planetary orbits, coming close enough to directly perturb the worlds we call home? This scenario is not purely hypothetical. It is a real possibility, governed by the same statistical principles that govern all random encounters in a crowded galaxy. Stars pass close to each other all the time. Usually, close means thousands or tens of thousands of astronomical units, far enough that only the loosely bound outer reaches of a solar system are affected. But occasionally, purely by chance, a star will pass much closer. The probability of a star passing within 1 AU of the Sun, close enough to directly affect Earth's orbit, has been estimated at approximately 1 in 100,000 over the next 5 billion years. These are long odds, to be sure, but they are not zero. And over the vast timescales of cosmic evolution, events with 1 in 100,000 probabilities eventually happen. If such an encounter occurred, The consequences for Earth would be catastrophic beyond anything in human experience. Let us imagine the scenario unfolding. Somewhere in the depths of space, an ordinary red dwarf star, perhaps half the mass of our Sun, perhaps less, is moving on a trajectory that will bring it through our solar system. We would detect this star long before it arrived, of course. Modern astronomy can track the positions and velocities of billions of stars with extraordinary precision. We would know, perhaps thousands of years in advance, that a visitor was coming. At first, the approaching star would be just another point of light in the sky, too dim to see without instruments, indistinguishable from the countless other faint stars scattered across the heavens. But year by year, decade by decade, it would grow brighter and closer. Its proper motion across the sky would increase as it approached, creeping from constellation to constellation, a moving point among the fixed stars. Eventually, it would become visible to the naked eye. A new star where no star had been before, growing brighter with each passing month. Astronomers would track its approach obsessively, calculating its trajectory with ever-increasing precision, confirming and reconfirming what everyone already knew. This star was coming straight for us. In the final years before closest approach, the intruder would dominate the night sky. Growing from a dim point to a brilliant orange beacon, it would eventually outshine every planet and every star, becoming visible even in broad daylight. At night, it would cast shadows, an eerie, ruddy light bathing the landscape in colors no human had ever seen from the sky. The visual spectacle would be magnificent and terrifying in equal measure. And then, over a matter of months, the star would pass through the inner solar system and begin receding. The brilliant intruder would start to shrink, dimming slowly as it departed. Those on Earth might breathe a sigh of relief, thinking the danger had passed, but the danger would only be beginning. The gravitational tug of the passing star would have altered Earth's orbit in ways that might not be immediately apparent. Perhaps Earth would be accelerated, gaining velocity and spiraling outward from the Sun. Perhaps it would be decelerated, falling inward toward the hotter inner regions. Perhaps, most dramatically, it would be flung entirely free of the Sun's gravitational grip, ejected from the solar system to become a rogue planet wandering the darkness between stars. Let us follow that most dramatic scenario. In the months following the star's passage, Earth's trajectory would gradually diverge from its familiar orbit. The Sun, once a constant presence defining day and night and seasons, would begin to appear smaller in the sky. Not dramatically at first. The change would be subtle, noticeable only with precise instruments. But as weeks became months and months became years, the shrinking would become unmistakable. The Sun would be receding, or rather, Earth would be receding from the Sun, flying outward on a trajectory that would never bring it back. The temperature would begin to drop almost immediately, though the rate of cooling would depend on how quickly Earth was departing. If the ejection were gradual, playing out over decades or centuries, the cooling would be similarly gradual, a slow slide into permanent winter. If the ejection were rapid, the temperature could plummet within years. Let us assume a relatively rapid ejection, Earth crossing Mars's orbit within a few years of the star's passage, Jupiter's orbit within a decade or two, Pluto's orbit within a century. As Earth passes the orbit of Mars, roughly 1.5 AU from the Sun, the average global temperature would plummet to approximately -50 degrees Celsius. This is colder than anything most humans have experienced, but not impossibly so. Antarctic research stations have recorded temperatures approaching these levels. With sufficient preparation, heated shelters, stockpiled fuel, preserved food supplies, Some humans could survive at this stage, but survival would be a desperate scramble. Agriculture would be impossible. Most plants would be dead or dying. Livestock could not survive outdoors. The entire infrastructure of civilization, designed for a world where the sun provided warmth and energy, would be failing. People would crowd into heated refuges, burning whatever fuel they could find, knowing that the worst was yet to come. By the time Earth reaches Jupiter's orbit, approximately 5 AU from the Sun, surface temperatures would sink to negative 150 degrees Celsius, colder than the coldest temperature ever recorded on Earth, colder than the surface of Mars, colder than anything in human experience. The Sun, still the brightest object in the sky, would be a pale yellow dot offering light, but almost no perceptible warmth. At these temperatures, survival on the surface would be impossible without extraordinary measures. Anyone still exposed to the environment would die within minutes. The cold would be not merely uncomfortable, but instantly lethal, flash freezing exposed flesh, crystallizing the water in blood and tissue. The oceans, already frozen on their surfaces, would continue to freeze deeper. The ice sheet covering the waters would thicken year by year, century by century, eventually reaching depths of kilometers. The water beneath would remain liquid, protected by the insulating ice above and warmed by geothermal heat from below. But the surface world would be unrecognizable. From space, Earth would look like an icy moon, the blue and green and white of the living planet replaced by the uniform gray-white of frozen death. No clouds would form. No weather would disturb the stillness. The planet would lie silent and seemingly lifeless, wrapped in ice under a darkening sky. As Earth approaches the orbit of Pluto and the Kuiper Belt, around 40 AU from the Sun, temperatures would drop to barely 40 degrees above absolute zero, approximately negative 233 degrees Celsius. At these temperatures, something strange and terrible would begin to happen to the atmosphere itself. The gases that make up our air, nitrogen, oxygen, argon, carbon dioxide, remain gaseous only because Earth's surface is warm enough to keep them that way. As the temperature drops below their condensation and freezing points, these gases would begin to change state. First would come droplets of liquid air, a phenomenon unlike anything in human experience, though it has been imagined in science fiction. Fritz Leiber's 1951 story, A Pail of Air, describes survivors of a rogue Earth scooping frozen oxygen from the ground and warming it over fires to breathe. The reality would be even stranger, the air literally condensing into mist, then rain, then snow, coating every surface in a layer of frozen atmosphere. Nitrogen condenses at negative 195 degrees Celsius and freezes at negative 210 degrees. Oxygen condenses at negative 183 degrees and freezes at negative 218 degrees. As Earth's surface dropped below these thresholds, the atmosphere would literally fall out of the sky, first as liquid droplets, then as crystalline snow, accumulating on the surface in a layer perhaps 10 meters thick. The sky would empty. Where once there was air, there would be almost nothing. A thin whisper of unreactive gases too sparse to constitute a real atmosphere. Stars would be visible during what had once been day, their light no longer scattered by atmospheric molecules, shining down on a world wrapped in frozen air and ice. The frozen corpses of every plant and animal that once lived on the surface would be buried beneath layers of nitrogen and oxygen snow, preserved in the terrible cold like specimens in some cosmic freezer. The cities of human civilization would lie entombed, their ruins covered in drifts of frozen atmosphere, monuments to a world that no longer existed. And Earth would continue outward, leaving the solar system entirely, becoming a rogue planet, one of billions, perhaps trillions, drifting through the galaxy without stellar companionship. The journey would be long beyond human comprehension. Traveling at approximately 30 kilometers per second, its velocity at the moment of ejection, Earth would cover about 900 quadrillion kilometers in 1 billion years. That's roughly 100,000 light-years, enough to cross the entire Milky Way galaxy. In that time, Earth would pass within a few light-years of thousands of stars, perhaps millions. The surface would be dead, frozen, buried under crystallized atmosphere. But remember what we discussed earlier. The deep ocean would survive. Miles beneath the frozen surface, protected by kilometers of ice, warmed by hydrothermal vents powered by Earth's radioactive core, liquid water would persist. And around those vents, communities of chemosynthetic organisms would continue their ancient cycles of life and death, utterly unaware that anything had changed above. For billions of years, life would persist in the deep dark, passengers on a frozen spaceship carrying them through the void, waiting, perhaps, for something to change. And something might. But before we turn to that hope, let us linger a moment longer on what would be lost. The ejection of Earth from the solar system would be, by any measure, the greatest catastrophe in the history of life on this planet. Greater than the asteroid that killed the dinosaurs, greater than the Permian-Triassic extinction that wiped out 90% of marine species, greater than anything we can easily imagine, because it would be the end, not just of one era of life, but of the entire surface biosphere that has existed for billions of years. Every forest would die. Every grassland would wither. Every coral reef would freeze. Every bird, every mammal, every insect, every fish that depends on sunlight or photosynthesis would perish. The complex web of life that has evolved over 4 billion years would be simplified to its most primitive components. The chemosynthetic organisms that never needed the sun in the first place. Human civilization would be among the casualties. Our cities, our cultures, our languages, our art, our science, our history, all of it would end. The vast majority of human beings would die, probably within the first year or two of the ejection. Those who survived in geothermal refuges or nuclear-powered bunkers might persist for decades, centuries, perhaps millennia. But eventually, they too would succumb to equipment failures, resource depletion, or simple attrition. Everything we have built, everything we have created, everything we have dreamed and hoped for would be frozen in time, preserved under layers of crystallized atmosphere like insects in amber. Future visitors to this frozen world, if any ever came, would find a planet-sized museum of a species that once reached for the stars, but was cut down by cosmic chance before achieving its full potential. This is the tragedy of the ejection scenario, not just the death of individuals, but the end of a story that had barely begun. Humanity is young. We have existed for perhaps 300,000 years as a species, developed agriculture barely 10,000 years ago, invented writing perhaps 5,000 years ago, launched spacecraft less than 70 years ago. We are children, cosmically speaking, children who have just begun to explore our neighborhood, just begun to understand our universe, just begun to develop the capabilities that might one day allow us to spread beyond this single fragile world. To be cut down now, or at any point in the next few million years, would be to lose not just what we are, but what we might have become. And yet, even in this bleakest of scenarios, there are reasons for hope, reasons we have been building toward throughout this journey. we have journeyed through scenarios that range from the inevitable to the improbable, from the sun's guaranteed death 5 billion years hence to the unlikely but possible ejection of Earth from its solar home. We have frozen the oceans, darkened the skies, and extinguished photosynthesis. We have buried civilizations under drifts of crystallized air and watched the last surface life succumb to cold beyond imagination. And yet, at every turn, we have found reasons for hope. This is perhaps the most remarkable conclusion we can draw from our exploration of cosmic catastrophe. Life is extraordinarily resilient, and the universe provides more opportunities for survival than our intuitions might suggest. Consider what we've learned. Even if the sun disappeared instantly, an impossible event, but a useful thought experiment, Earth would not become a dead world. Deep in the oceans, around hydrothermal vents powered by radioactive decay in Earth's core, chemosynthetic ecosystems would continue to thrive for billions of years. These organisms have never depended on the sun. They wouldn't notice it was gone. Their descendants might still be swimming in warm water long after our current biosphere has become an ancient memory. Even if Earth were ejected from the solar system, becoming a rogue planet wandering the darkness between stars, those same deep ocean ecosystems would persist. The ice above would insulate them. The geothermal heat below would sustain them. Life would go on, diminished but unbroken, for timescales that dwarf the entire history of complex life on Earth's surface. And this is just Earth, one small rocky planet around one ordinary star. The universe is filled with worlds we've never seen and may never see, many of which might harbor similar refugia for life. There may be billions or even trillions of rogue planets wandering our galaxy alone, worlds ejected from their parent systems or formed independently in the darkness between stars. Some of these worlds almost certainly have internal heat sources, whether from radioactive decay, primordial thermal energy, or tidal interactions with captured moons. Some of them might have subsurface oceans. Some of those oceans might host hydrothermal vents, and some of those vents might support chemosynthetic ecosystems, much like the ones we've discovered on Earth. If life can exist without a sun on Earth, it can exist without a sun elsewhere. The vent communities at the bottom of our oceans prove that the most essential requirements for life, liquid water, chemical energy, and stable conditions, can be met without any reference to stellar radiation whatsoever. This realization expands the potential domain of life in the universe by an almost incomprehensible margin. We have traditionally focused our search for life on planets in the habitable zone of their parent stars, that narrow band of orbital distances where temperatures allow liquid water on the surface. But if life can thrive without stellar input, then habitable zones become almost irrelevant. Subsurface oceans on icy moons, deep ocean ecosystems on rogue planets, chemosynthetic communities on worlds we've never imagined. All of these become candidates for life, regardless of their relationship to any star. Some researchers have suggested that planets with subsurface oceans might be 100 to 1,000 times more common than rocky planets in traditional habitable zones. If even a fraction of these worlds harbor life, then living organisms could be far more abundant in the universe than our sun-centric assumptions have suggested. The Milky Way might be teeming with life, not basking under the light of stars, but hidden in the dark, warmed by planetary cores, thriving in environments we would have considered lifeless just a few decades ago. And there is an even more hopeful possibility to consider. If Earth were ejected from the solar system, it would not wander the void forever. Moving at 30 kilometers per second, it would cover vast distances over cosmic timescales, passing near thousands of stars over billions of years. potentially millions over the full lifetime of our rogue journey. Most of these stellar encounters would be too distant to matter. But occasionally, perhaps once in millions or billions of years, Earth might pass close enough to another star to be gravitationally captured, pulled into orbit around a new sun, thawed by new warmth, restored to something like its former state. It's a slim hope, statistically speaking. The probability of being captured by any individual star is extremely low, and even if capture occurred, the resulting orbit might not be suitable for surface life. But over billions of years and countless stellar encounters, the cumulative probability becomes meaningful. It's not impossible that a rogue Earth could find a new home. And if that happened, if Earth's frozen surface slowly thawed under the light of a new sun, if the crystallized atmosphere sublimated back into gas, if liquid water once again flowed across the continents, the chemosynthetic organisms that had survived in the deep ocean for billions of years might have an opportunity to recolonize the surface. Life on Earth might get a second chance. Perhaps those surface organisms would evolve intelligence, developing over millions of years into beings capable of technology, science, and exploration. Perhaps they would dig into their planet's crust and discover the frozen ruins of an earlier civilization, cities preserved under kilometers of ancient ice, artifacts flash frozen at the moment of catastrophe, records of a species that once called this world home. They might find our libraries, our artwork, our scientific instruments. They might decode our languages and learn our history. They might discover that they are not the first intelligent species to walk this world, that billions of years before their emergence, another civilization had risen, flourished, and been lost to cosmic disaster. What would they think of us? Perhaps they would marvel at what we accomplished in our brief tenure on Earth's surface. Perhaps they would learn from our mistakes. Perhaps they would feel a kind of kinship with being separated from them by an abyss of time so vast that the sun itself had died and been replaced. Or perhaps no such resurrection would occur. Perhaps Earth would wander the void forever, its surface permanently frozen, its deep ocean life continuing its ancient cycles in perpetual darkness, never knowing that above them lay the remains of a world that once basked in sunlight. Even that outcome has a certain beauty to it. Earth as a spaceship, carrying living passengers through the cosmos for billions of years. Earth as a seed, bearing the potential for life across unimaginable distances. Earth as a monument, preserving the record of 4 billion years of evolution in ice and rock and frozen atmosphere. We tend to think of cosmic catastrophes as endings, the destruction of everything we know and love, the extinction of our species, the death of our world. And in one sense, that's exactly what they are. The scenarios we've explored in this journey would end human civilization as we know it. Most or all of the humans alive today would die. The surface biosphere we depend on would be destroyed. But endings are also beginnings. The matter that makes up our bodies, our cities, our entire world was forged in the cores of ancient stars that exploded billions of years ago. The carbon in our cells, the oxygen in our lungs, the iron in our blood, all of it was created in stellar furnaces and scattered across the cosmos by supernovae. We are, quite literally, made of star stuff. When the sun dies, that matter will be recycled once again. The atoms that were briefly arranged into human beings and redwood trees and coral reefs will be returned to the cosmic medium, eventually to be incorporated into new stars, new planets, perhaps new forms of life. Nothing is truly lost. Everything is transformed. This is the cosmic perspective that emerges from our exploration of stellar death and planetary catastrophe. We are temporary arrangements of eternal matter, brief patterns in the endless flux of cosmic evolution. Our individual lives are short, our civilization is young, and even our species is a recent phenomenon on the scale of cosmic time. But the processes that created us will continue long after we're gone. Stars will form and die, planets will coalesce and be destroyed, life will emerge, evolve, and perhaps go extinct, only to emerge again in new forms on new worlds. The universe is not a static backdrop for human drama. It is a dynamic, evolving system of which we are a tiny but meaningful part. 5 billion years from now, when the sun swells into a red giant and consumes the inner planets, the matter that once was Earth will be scattered into space, seeding the interstellar medium with the elements of life. Some of that matter may eventually be incorporated into new solar systems, new planets, perhaps new living beings. In that sense, we are not separate from the cosmos. We are an expression of it. The same forces that will one day destroy our world are the forces that created it. The same stellar processes that threaten us with extinction are the processes that made our existence possible in the first place. There is something profoundly humbling about this realization, but also something strangely comforting. We are not alone in the void, cast adrift in a hostile universe. We are woven into the fabric of cosmic evolution, participants in a story that began 13.8 billion years ago and will continue for trillions of years into the future. What matters, perhaps, is not whether we survive every possible catastrophe, but what we do with the time we have. What knowledge do we create? What beauty do we bring into the world? What legacy do we leave for whatever comes after us? The hydrothermal vent communities at the bottom of Earth's oceans will carry on regardless of what happens above. They don't create art or write poetry or wonder about the stars. They simply exist, persisting through eons, indifferent to the fate of civilizations. But we are different. We are the part of the universe that has become conscious of itself, that can contemplate its own existence and ask questions about its meaning. We are the cosmos examining itself, wondering at its own nature, reaching out toward the stars. If we are wise, we will use our brief moment of consciousness to learn as much as we can about the universe that created us. We will explore our solar system and eventually venture to other stars. We will preserve our knowledge against the possibility of catastrophe, ensuring that even if our species perishes, something of what we learned and created might survive. We will look up at the night sky, at the stars that are constantly moving, occasionally approaching, always beautiful, and we will feel not fear but wonder. Wonder at the vastness of it all, wonder at our improbable existence, wonder at the cosmic processes that gave us life and will one day take it away. The sun will die. Gliese 710 will approach. Stars will continue their endless dance through the galaxy, occasionally disrupting each other's planetary systems, occasionally creating new opportunities for life. Earth may persist for billions of years more, or it may be lost to some cosmic accident we cannot predict. But in this moment, in this brief, precious now, we are alive, we are aware, we are capable of understanding our place in the cosmic story, even as we acknowledge our inability to control its ultimate outcome. That understanding is perhaps the greatest gift the universe has given us. The ability to look out at the stars and comprehend, even dimly, what we're seeing. The capacity to imagine scenarios billions of years in the future, to empathize with organisms we've never met, to feel connected to processes that will continue long after every trace of our existence has been erased. We are made of star stuff, and to the stars we will return. What happens in between is up to us. The sun will not live forever, but neither does it need to. Its light has already given rise to something remarkable, a species capable of wondering about its own existence, of reaching out toward the cosmos, of finding beauty and meaning in a universe that seems, at first glance, to be utterly indifferent to human concerns. Perhaps that is enough. Perhaps in the end, that is everything. The story of the sun's death is not a tragedy. It is simply the next chapter in a cosmic epic that has been unfolding for billions of years and will continue for billions more. We are privileged to be here to witness even a tiny fragment of it. As always, thank you for joining me on this journey through the cosmos. The universe is vast, ancient, and full of wonders we are only beginning to understand. May we never lose our sense of awe at the incredible privilege of being alive to explore it, and may whatever comes after us, whether descended from humans, from the extremophiles in our oceans, or from sources we cannot imagine, carry forward the spark of curiosity and wonder that has brought us this far. The stars are waiting. The journey continues. What then should we take away from this exploration of cosmic catastrophe? First, and most fundamentally, perspective. The timescales we have discussed, millions of years, billions of years, are so far beyond human experience that they can seem almost meaningless. Our lives span decades. Our civilizations span millennia at most. Even our species has existed for only a geological eye blink. To think in terms of millions or billions of years requires a kind of imaginative leap that does not come naturally. But making that leap is valuable, even essential. It reminds us that the cosmos operates on its own schedule, indifferent to human concerns and human timescales. The sun will die whether we want it to or not. Stars will pass close to our solar system whether we prepare or not. The geological and astronomical processes that shape our world operate continuously, inexorably, regardless of what happens on any individual planet's surface. This perspective can be humbling, even terrifying, if we dwell too long on our cosmic insignificance. But it can also be liberating. If we cannot control the ultimate fate of the universe, we are free to focus on what we can control: how we live our lives, how we treat each other, what knowledge we create and preserve, what beauty we bring into the world. Second, appreciation. Every day that the sun rises is a gift, not in any mystical sense, but in the simple, physical sense that the conditions necessary for our existence are temporary and will not last forever. The warmth on your face, the blue sky above, the green plants converting sunlight into the oxygen you breathe, none of this is guaranteed. All of it depends on a fortunate arrangement of cosmic circumstances that will eventually change. To live with awareness of this impermanence is to appreciate more deeply the world we have. Not to live in constant fear of its loss, but to recognize its value, its fragility, its preciousness. The sunset you watch tonight is one of a finite number you will ever see, not because of cosmic catastrophe, but simply because life is short. The knowledge that our entire world is similarly finite on a grander scale can deepen our appreciation of every moment we're privileged to experience. Third, responsibility. If we are the part of the universe that has become conscious of itself, if we are the cosmos looking back at its own nature, asking questions about meaning and existence, then we have a unique responsibility to use that consciousness wisely. We are stewards of something precious, The accumulated knowledge of our species, the cultural heritage of thousands of generations, the scientific understanding that has allowed us to comprehend our place in the cosmos. That heritage deserves to be preserved and extended. Not because we can guarantee its survival, we cannot, but because the act of preservation is itself meaningful. Every piece of knowledge we pass to the next generation, every work of art we create and share, every question we ask and answer, adds to the sum of human understanding. That sum may eventually be lost, but its existence, however temporary, matters. Fourth, hope. This may seem paradoxical after a journey through cosmic catastrophe, but it is perhaps the most important takeaway of all. The universe, for all its dangers, provides more opportunities for life and meaning than our intuitions might suggest. Rogue planets can harbor life. Chemosynthetic ecosystems can thrive without stars. Ejected worlds can potentially be recaptured by new suns. Life, once it arises, proves remarkably difficult to extinguish entirely. And intelligence, once it develops, has the potential to spread beyond its world of origin, to take root in new environments, to persist through catastrophes that would end any single planet's habitability. We are not helpless in the face of cosmic danger. We can detect approaching stars and prepare for their passage. We can track asteroids and develop technologies to deflect them. We can build refuges and store knowledge and develop the capabilities for interstellar travel. We cannot prevent every possible catastrophe, but we can significantly improve our odds of surviving those that do occur. And if we spread beyond Earth, if we establish settlements on Mars, on the moons of Jupiter and Saturn, in rotating habitats throughout the solar system, eventually around other stars, then no single catastrophe can end the human story. We would become resilient against precisely the kinds of cosmic dangers we've explored in this journey. That spreading is not guaranteed. It requires sustained effort, technological development, social cooperation, and a long-term perspective that does not come naturally to our species. But it is possible, and if we achieve it, we will have transcended the single greatest vulnerability we currently face, our dependence on one small planet around one ordinary star. The cosmos is vast, ancient, and often hostile, but it is also beautiful, mysterious, and full of opportunities we are only beginning to explore. The same universe that will one day kill our sun also gave birth to it. The same processes that threaten us with extinction also created us. We are children of the cosmos, and to the cosmos we will return. But in the meantime, we have the extraordinary privilege of being alive to witness its wonders. 5 billion years from now, when the sun swells into a red giant and begins its final transformation, the matter that currently constitutes Earth, including the matter that currently constitutes you, will still exist. It will be scattered across space, incorporated into new stars and planets, and perhaps new forms of life. The atoms that are temporarily arranged into your body have existed for billions of years and will exist for billions more. You are, in a very real sense, eternal, not as an individual consciousness, but as a pattern briefly manifested in matter that will endure long after that pattern has dissolved. This is not immortality in any traditional sense, but it is a form of continuity, a connection to the cosmos that transcends individual existence. The carbon in your cells was forged in ancient stars. The oxygen you breathe was released by photosynthetic organisms billions of years ago. The iron in your blood was created in supernovae that exploded before the sun was born. You are made of star stuff, and star stuff you will remain. long after the stars currently shining have burned out and new stars have taken their place. This cosmic perspective does not diminish the value of individual lives. If anything, it enhances it. Each of us is a unique arrangement of cosmic matter, a pattern that has never existed before and will never exist again. Our experiences, our relationships, our creations, all are irreplaceable, precisely because they are temporary. The transience that might seem to rob life of meaning is actually what gives it meaning. A life that lasted forever would eventually exhaust all novelty, all growth, all change. It is precisely because our time is limited that each moment matters. The same is true of our species, our civilization, our world. Earth will not last forever. Humanity may not survive the next 1,000,000 years, let alone the next billion. But the existence of our species, however brief on cosmic timescales, is meaningful precisely because it is unique. We are the first intelligent species to emerge on this planet, perhaps the first intelligent species in this corner of the galaxy. What we do with our moment of awareness matters, whether or not anyone remembers it in 1,000,000,000 years. So let us use our moment well. Let us explore what we can, discover what we can, create what we can, love who we can. Let us preserve our knowledge and extend it, pass it forward to future generations who may face challenges we cannot imagine. Let us look up at the stars with wonder rather than fear, appreciating their beauty even as we understand the dangers some of them pose. The sun will die, but not today. Today, it still shines, still warms our world, still powers the biosphere that sustains us. Today, we are alive, conscious, capable of wonder and discovery and love. Today, we are the universe experiencing itself, the cosmos contemplating its own nature. Tomorrow will bring its own challenges. Eventually, a tomorrow will come when the challenges are too great, when the sun fails or a star passes too close, or some catastrophe we cannot foresee brings the human story to its end. But that tomorrow is not this day. This day is ours. Let us make the most of it. As always, thank you for joining me on this journey through the cosmos. The universe is vast, ancient, and full of wonders we are only beginning to understand. May we never lose our sense of awe at the incredible privilege of being alive to explore it. And may whatever comes after us, whether descended from humans, from the extremophiles in our oceans, or from sources we cannot imagine, carry forward the spark of curiosity and wonder that has brought us this far. The stars are waiting, the journey continues, and for now, at least, we are here to witness it. Thanks for watching.